Okay. But I also feel like it's like we those are not next person's slides. Okay. Yeah.
Okay, it's working. Okay, good morning, everyone. Now we can start. So we are in the session on dark matter in galaxies across the cosmic time. And today our session is about observational constraints on dark matter in galaxies. And our overview talk will be given by Sadhana Price from University of Pittsburgh. And it's about, of course, observational constraints on dark matter across 10 billion years. Okay, so here is she.
Sorry.
Good morning, everyone. I'm so excited to be here and be invited to be here. I will admit, so unfortunately, in the interest of time, I can't do a full, thorough review. So I will apologize ahead of time if I've missed highlighting some of the work that you've been working on. But of course, we will hear from all of you. But I wanted to take the opportunity with a slightly extended talk period to sort of, one, lay the stage on some of a bunch of these observational constraints of galaxies of both the luminous matter, which does important for trying to then understand the dark matter, and then some of the work that I've been involved with for trying to constrain dark matter within galaxies. So I'm going to talk a little bit about some of the work I was involved with the MOSDEF survey, but primarily I'm going to talk about work that I've been involved with collaborators at the MPEIR group and the SIN, ZC-SYNTH, KMOS 3D, FIBS, and NOEMA 3D teams. So, a whole slew of people, some of which are at this focus meeting this week. Okay, so to start out with things that I think we all sort of are familiar with, but I just like to set the stage. My interest in dark matter and learning about this is sort of through the view of trying to understand galaxy evolution. So, in that context, dark matter is a key ingredient in really trying to understand how galaxies are growing and evolving. So this sort of prevailing paradigm is that you have galaxies that grow within a dark matter halo, and they're growing by, you've got accretion and material coming in, you've got internal evolution, you've got outflows that also, and feedback that's sort of also regulating this and coming into the whole picture. And of course, interactions and mixing this all together. And really, it's a very, intertied sort of set of processes. And so to try to detangle this, one of the key things that I love as an observational, extragalactic person is to be using these observations of galaxies and their halos over time to try to constrain these intertied process. And I will step back. I am going to probably say high redshift and high Z at some point. I mean, sort of redshift 1 to 3. I'm working now also with some other folks who work much higher redshift. So if I slip and say that, if I say, low redshift, I mean basically local and high redshift will be redshift 1 to 3. So please forgive me today. Okay. So, and also, something I think we all know, but okay, what sort of methods do we have to constrain mass in galaxy? I'm being sort of very, very brief here is, okay, for stars and things like that, you can do stellar population and SCD modeling, trying to get it, gas as well. If you have luminosity and conversion factors, trying to say how much gas mass do you have, this and that. But of course, you've got degeneracies. What if things are optically thick and dust and you've missed all the stars? And of course, what we've been describing as dark matter, you can't get any of that from this. And so what I'm talking about today is using kinematics as the probe of all of the mass that's enclosed. And really trying to leverage this to try to be able to say what parts of this, where is the galaxy of the normal matter, the baryons, the gas plus stars, and where is the halo, and sort of what is this interplay of the mass distribution within these galaxies. Okay, so as an observational astronomer, I almost have to put this out, but for context, for people who don't, work at cosmic noon all the time, so a brief history of cosmic time. So this is the cosmic star formation rate density, and versus redshift. And so overall, I think a lot of us are familiar with this, where we have this peak, is sort of between redshift 1 to 3. It's basically the galaxies on average were forming stars 10 to 20% higher, and then now, we're sort of this winding down epoch. Earlier, it was the accretion epoch winding up. And overall, so, hello. Measurements of, say, molecular gas fraction in galaxies also really rises towards this time. I think it's more, I think that this is not so updated. I think we're getting better measurements out here, but on average, galaxies at this epoch were, galaxies were becoming more and more gas rich. And this explains why you'd be forming stars much more rapidly, but it's sort of changing the properties of the galaxy, which then impact what we have to do to understand the dark matter. Okay. So, and I particularly always love cosmic noon here, this peak. And so just as context, the Milky Way was basically galaxies like the Milky Way were assembling about 70% of their stars during this epoch. So, what we see as galaxies today, specifically at the massive end, were really rapidly building up then. All right. So two other things I wanted to point out is that overall galaxy size is decreasing with mass. I know we know this, but it's, point tech away in putting together this picture. And then also there's a predicted decrease in dark matter halo concentration. So you would have less concentrated in the centers of galaxies. Now, we could try to actually probe this, but so here's sort of the picture of what I wanted to then lead into the work I've been involved with. All right. So the really, renaissance in this last decade there's been incredible optical near-infrared spectrographs that have really been letting us push into thousands and tens of thousands of relatively massive galaxies where we can get kinematic measurements for them. And through that, be probing the total mass and trying to get this question of dark matter. And so it's just been an incredible number of sort of observations. From seeing limited IFU observations, there's just been a whole slew of surveys, locally. Here I know folks are talking about MAGPIE at sort of redshift 0.3, cosmic noon, just a whole slew, particularly using the KMOS instrument, and other ones pushing towards even higher redshift. Of course, if you have adaptive optics assisted IFU, you have sort of hundreds of galaxies by now, over, again, a number of instruments and surveys. And of course, then even tens of thousands of galaxies using slits, which it's true if you have the full spatial information from an IFU, it's easier, but there are things we can learn from the slits, which are very helpful. And yeah, so it's just a whole slew. And really, it's getting all of these measurements. It's really letting us try to answer the question of population-wide. What's happening, not just in an individual galaxy, because for me, I always look at one galaxy and go, this is really cool, but how representative is this? How much scatter is there in the overall population? And so it's been really exciting to move into this era where we can have comprehensive censuses of kinematics in galaxies. Okay. And of course, also there's submillimeter interferometry. I am not focusing on that today, but this has also been a way of getting at this kinematic measurements. And I know some other folks are going to be talking about today and in our talks again on Thursday. Okay, so walking through again, finally finishing this picture of the luminous matter, which I argue is important to then start understanding the dark matter. So some of these observations, particularly with Hubble imaging, is, okay, massive star-forming galaxies are on average looking, they look kind of clumpy and weird, but if you actually look at their light profiles, they're looking more disk-like in the sense that they have surface indices like 1. But okay, you're kind of like, do I really believe that? But if you do stellar population synthesis modeling to try to back out their stellar mass, they actually look much more smooth and actually are looking like they're having very massive bulges towards the more massive end. And actually, we don't have a new plot of this, but this is actually really nicely backed up now with imaging coming out of JUICE-T. We're basically directly probing the rest frame near infrared, almost getting direct pictures of the stellar mass in those galaxies. So, okay, these things look like they are disks and, you're growing massive bulges to the very massive end for these star-forming galaxies. And of course, also what some of this IFU observations, particularly from the KMOS 3D survey, highlighting here, we're revealing is that many of these massive galaxies look like they're having rotating disks. Now, at least particularly in their ionized gas, this is more elevated random motions, more turbulent. There's some hints for at least some of these that they also have somewhat elevated dispersion in the colder gas. But overall, maybe not exactly like what we have in our very nearby galaxies in our own Milky Way. Okay, so this is the context I wanted to lay because, of course, some of these choices are really important for then trying to model and understand dark matter. Okay, what was some of the early works and some of our early attempts? Well, you can try to say, I want to measure a dynamical mass, and then I will make a separate measurement of the baryonic, the gas and stellar masses. And you can do this in sort of, I will categorize this roughly in two ways. This is the most common. You could do a dynamical mass from single mass component modeling, or you could try to say, I'm getting a single set of velocity measurements, and I will try to use a sort of quote unquote virial factor. And so this is some of the work that Stein-Zatz led. And so basically doing this comparison of the baryonic mass versus dynamical mass, so sort of dark matter fraction increasing down here, and seeing evidence that the galaxy scale, so this is within the effective radius of the galaxy, sort of where the light is, half of the light of the galaxy is, so not extended out further, is getting much lower towards higher redshifts. Now, of course, some of my own work did this. And actually, so what they've measured here is only in the large galaxies where you're above sort of 2 kiloparsecs. And we actually had very similar agreement. This is with slit spectra versus IFU here. Of course, so here is one of the things I'll come back to later, one of the hints of, oh, this is challenging. For our really small galaxies, we're getting things firmly in this, that baryonic mass is higher than the dynamical mass. And really what I think this says is, most of the systematics for measuring the dynamical mass would actually not make it any better. But what it might be is that it's a challenge to actually be fully probing the inner parts, so the dynamics of the inner part of the galaxy. So really these dynamical measurements might sort of be fundamentally flawed because they're not deep enough for these small galaxies and or because they were seeing limited. So, okay, a preview of some of the sort of challenges as I see it, having thought really hard about this paper. Okay, so one of the other ways, so the takeaway here, at least, was this was the hints from some of the work that I was involved with and others were involved with in 2016, was that massive galaxies, so this basically 10 to the 10 and kind of above on average, are baryon dominated within their effective radius at the sort of cosmic noon epoch. Okay, so a very specific statement on a mass range and the redshift range. And there's also, a number of other folks who were involved with measurements that's sort of similar to this and are, related to trying to build to even making these measurements. And I'm going to shout out to that. But one thing I do want to highlight and as a person in the field is interpreting this has been, making sure we're all talking about what radius we're talking about, because I know some other measurements have preferred to talk about larger physical apertures, and that's great. But it's like you got to make sure we're comparing apples to apples when we're trying to put together the picture. So, okay, aside caution there. So, well, okay. But this is required that we are trying to do something with the dynamical mass and trying to say we have a handle on our gas and stellar mass. And I mentioned earlier that, of course, do we understand stellar population synthesis? Do we understand how to measure gas masses? Are there challenges on that? Well, if you get deeper data, you could try to do this in actually just a dynamical way. Or if you're really pushing out to the galaxy outskirts and into their halos with deep spectra sort of pushing out beyond this where the light is dominating from the galaxy, you could try to be saying, okay, could we get this information just from the halo? Okay, I think the answer is no. You still need priors of information of what we know about the light and luminous matter in the galaxy, which is why I belabored early sort of the view of what we've learned about galaxies epoch. And so kind of using measurements of the rotation velocity of galaxies and also the velocity dispersion profile. So this is from an IFU cube and then extracted in slits and trying to say, okay, great, let's try to model this. So, and by going out to very large radii and understanding what your observational effects are, trying to get this handle on detangling these components. So, one of the big things that I was involved with recently with the MPEIR group was this sort of project we were calling RC100, where we were compiling 100 galaxies with really deep spectra from IFU. There's a couple with really well-aligned slits. A couple of these are also CO data. going out to having kinematic measurements out past at least 1.5 effective radii. And so these 100 galaxies had a total of basically almost 1,400 hours of observation time, a median of about 11 hours total. A lot of this is drawn from the KMOS 3D survey, so we were getting a bunch of them at once. So there was multiplexing, but it's still, this is a culmination of a very large sets of surveys to try to put this together and trying to say, okay, let's do a nice census of this more massive end and try to do this outskirt dynamical modeling approach. Okay, so, and what I mean by that is, again, sort of just to anchor this in a little bit of context to say, okay, great, if we've measured, if we have measurements out past the effective radius, and towards larger radii, we could try to be saying, okay, if we had a component that was the baryons, what would their velocity signature be? What would their contribution be? What's the dark matter contribution be? And have the constraints on the total circular rotation velocity. So, okay. And the way we've really been approaching this, particularly for this RC100 epoch, is the most recent incarnation of some of the dynamical modeling code that the IR group has been involved with. So Lillian Lee has been really involved with part of this too, and she's talking later. But so the idea was, okay, we're going to take a bunch of mass models. So parametric mass models, but informed by some of these other observations. So you have a disk, maybe a thick disk, a massive bulge, with a physical extent, a dark matter halo, a velocity dispersion and pressure support for the ionized gas or the cold gas. Actually, this code will support things like non-circular motions and separate light profiles and black holes. And so actually, there's a whole bunch of things we've cooked in there that we are not using for this particular project. But what we would do is we'd say, okay, we're going to take these intrinsic parametric models of the mass and the velocity components, and we're going to put it together into an intrinsic galaxy model. And then what we do is we forward model, so including all the observational effects. So first starting into a hypercube where you've got X, Y, Z in spatial dimensions, and then also the wavelength dimension, collapsing it along the line of sight, doing your beam smearing, doing your instrumental line spread function, all of that, and basically getting what would be a noise-free IFU cube model. And then what we could choose to do is either, we could try to fit to the data by taking that IFU cube and extracting from it. Either extracting in the same way as the data and, or either 1D, 2D, or you could try to fit in 3D. For this RC100 project, we really focused on trying to do in the 1D slits, so we could try to flare them to get the maximum signal to noise towards the higher radii. All right, so, and this is the code DismalPy, and actually it's publicly available now. There's the website. I'd be happy to point you at that later. Lillian will have a link to this later too. All right, so, and I have, of course, mistimed things a little bit. So what do we have found with this? So Amit Nestor, one of our collaborators, was the one leading this RC100 paper. And so on average, we were finding that the dark matter fraction within the effective radius for these massive galaxies is decreasing with redshift, sort of actually in nice agreement with what Steinmautz's paper, observations we're doing, and actually sort of hinting that it might be similar to some predictions from TNG 100 for the really massive end, but sort of maybe a little bit of tension. We got to fully track down the mass matching there. Okay, broad picture on that. But I want to walk this out to a different sort of parameter space of looking at this. And so comparing the dark matter fraction within the effective radius versus the galaxy scale baryon mass surface density. So just, how much mass have you got shoved within that effective radius? And we actually see this really nice anti-correlation. And we see this both for our RC100 observations and for the sort of fit to the data from Steinmautz's work. So one thing to note here is for our RC100, basically almost half of these galaxies would satisfy the definition of a maximal disk locally. Sort of just an aside there. But that overall, what we see here is it actually, it overlaps with the redshift 0 late type galaxies sort of at this one end, which actually we have more of our redshift 1 galaxies sort of up here, versus this, a lot of these higher redshift galaxies overlap with these measurements of local early type quiescent galaxies, ellipticals. Interestingly, actually, this is a little bit offset from measurements of stellar kinematics of quiescent galaxies at redshift 1.7 from the Virial survey. So maybe actually, because to point out, These galaxies, most of these galaxies are so massive, they will probably quench soon. And so they might actually be close progenitors to some of these quiescent galaxies. So maybe there's some interesting things in there. But overall, this picture of these are within their effective radius, they're not baryon dominated. Sorry, they are very baryon dominated, not dynamically dominated by any halo. Okay, so on average, this is sort of agreeing with some predictions from simulations, but maybe there's some nuances there to look at. And also I want to highlight there's some work that Nicolas Boucher led, looking at slightly lower masses and lower redshift that also looks within this framework. So connecting the galaxy and dark matter halo constraints. Well, okay, if we want to know what shape of a density profile do we have, the nice thing here is the galaxy kinematics give us that smaller scale. But what we can try to do is we can pair this with constraints from abundance matching. And what we've done is we've done this by sort of flipping this around. So now we're not looking at dark matter fraction, we're looking at dark matter surface density versus, again, this baryon surface density. It's sort of a way of trying to say, okay, so for our observations, they lie like this, but then we can take even each of these halo profiles and predict just analytically where would they lie within the space. And for a cuspy NFW halo, you'd lie here. For a chord halo where you have less dense, it's less dense in the center, it would be down towards there. And adiabatic contraction would sort of move you up here in this space. And a lot of our sort of galaxies are overlapping this chord profile space, particularly at that very baryon dominated end, which is sort of, okay, great. There's some evidence for chord halos. And actually there was some evidence for chord halos and also Nicolas Boucher's work. Some of these mechanisms that could cause this are, say, dynamical friction from inflowing material or rapid potential fluctuations, which also is the dynamical friction. And actually, there is some evidence that we're seeing some of these inflows in observations, but also sort of this is backed up. There could be some theoretical framework, which it seems like this could happen. So does it mean that dark matter by itself would form a core in these? No, but that this is maybe a picture of what's dynamically happening in these galaxies with their very rapid star formation and everything. And if, in their later time, maybe this, you could eventually have the halo collapse inwards and be more cuspy again. Okay, so I will briefly sort of finish here. I wanted to highlight sort of food for thought in discussions in the rest of the session is some results from comparisons between dynamical tracers. So mostly what I've been talking about is ionized gas tracers. So one for some galaxies that were observed both in KMOS 3D and in the legacy survey. So you have stellar kinematics. You have overall good agreement. And also in some galaxies where you have both ionized gas and molecular gas, you have fairly, good agreement in some of the inferred parameters. So there's, we're starting to try to say, are we getting the same answer in some of these tracers? That's, more complex, bigger samples are really going to nail that down and show us where the subtleties are. And of course, finally, there's a ton of challenges. So I know, I apologize my timing, but making sure we have deep enough data to probe the potential. So some of the work I was talking about with MOSDEF earlier, we have to also use other observations to break these degeneracies. Some of the comparisons between studies is going to be the choices of your mass parameterization. And of course, questions like how do you deal with pressure support corrections and everything like that. So, and I will leave that there.
You giving me questions? Yeah.
Thank you. Very nice talk and very interesting. So you showed us that in the redshift range that you observe, you have small galaxies, small spiral at the low redshift and more massive at the. So is it possible that when you look at the dark matter, you are more dominated by baryons because they are massive? And if you compare massive galaxies that equal zero only with massive, do you find the same thing? Because elliptical galaxies are not dominated by dark matter also.
Yeah. Interesting point. It's interesting for trying to even ask which ones are dominated or not. I think part of this parameter space is a great way to start looking at that. But yeah, I think maybe slicing and dicing our comparisons is a really interesting thing for the future. I know we're short on time. I apologize.
Yes. I came here to see the hands.
Okay, good. Good.
Hi, Sedona. So when these baryon-dominated disks, redshifts, high redshifts were first being published by Gensel a few years ago, it was sort of said that this is unexpected. And now we're seeing simulations starting to agree with that. So I'm wondering what's changed now in the simulations.
That's a great question. And I will admit, I do not remember. I would have to check that. And if there's simulators who know that, I would love to be talking more about this. Or maybe we can follow up more on Slack and I can try to double check that.
Yeah. I'm just looking at the plot there. There's a huge difference between magnetic and
yes,
CNG
and I'm
100.
trying to, I will admit I didn't do my homework quite as well. I think part of the challenge here is, right, a lot of this ends up buried in the subgrid physics scale in simulations. And so I think for magneticum, because it's a much more zoom individual galaxies, it's able to have better spatial resolution than even TNG 100. Because like, right, TNG 100 is great, but it is still fundamentally a much larger cosmological zoom simulation. And so it's not getting to quite as small, mass and physical scale. So yes, something in, improve being able to calculate at smaller scales and differences in the subgrid physics, baryonic physics is I think the answer. I would to double check.
Sorry, we cannot take any more questions. We are running out of time. Put them on the Slack, please. And thanks a lot for them again.
So this counter includes the time for the questions. So.
Okay. I should welcome everyone again because I see like a lot of people are here. Thanks for coming and joining us for Focus Meeting 9. And can we put the slides? Okay, so now we have Caro Foster from University of South Wales in Australia, and she will talk about, we don't have slides up there. She will talk about dynamical and morphological transformation of galaxies through cosmic time. Can we have the slides?
Forward, backward, pointer.
Great.
Forward, pointer.
Okay, thank you.
Thank you so much to the organizer and especially Gary for a really exciting program. I'm very pleased to be here. As Gary said, I'm going to be talking about the dynamical and morphological transformation of galaxies through cosmic time, or at least I bit off a whole lot more than I could chew in 12 minutes. So hopefully we get through some of it. This is my only background slide. I really apologize. This was just really to set the scene for the rest of the stuff I'm going to be talking about next. But I wanted to just use this to tease out one of the puzzles that kind of got me thinking about some of the questions that we have there. What is the role of environment in setting the dynamics of galaxies, right? We're talking about hierarchical assembly. Galaxies, you would think, would really care about the environment in which they grew up and are found today. And so in the late 2000s, early 2010s, we seem to have a really nice picture of galaxies that don't rotate or who are slow rotators, at least in the stellar kinematics, to tend to prefer denser environments in the local universe. A couple of years later, going to the ends of the 2010s, people found that or realized that if you accounted for mass at a given mass, there was no environmental trends. So it seemed that it was mass that was actually driving the dynamical or the stellar dynamics of these galaxies rather than environment. And it just so happened that more massive galaxies today are found in denser environments. And fast forward to today, there's been a slew of papers coming out now that actually have seen that, in fact, it is much more strongly correlated with star formation rate and age rather than even mass. So it's really when your halo started collapsing, you reach this density, you form the majority of your stars. That is what sets your spin parameter, at least it seems, okay? Which was puzzling to me. So what then, if any, is the role of environment in setting the dynamics of galaxies? For this, I'm turning to the MAGPIE survey. I don't have time to give the MAGPIE survey full justice. I have to thank Sedona for introducing it. As you could see, it's a redshift, it's an integral field spectrograph survey of 60 centrals and their immediate environment within 1 arc minute using MUSE. We're looking at overall, roughly 150 spatially resolved in the stellar and ionized gas kinematics galaxies at the highest possible redshift where you can get both of these probes. And so basically we're at redshift 0.3. That's roughly a third of the history of the universe. For those of you who deal with very high redshift, you might scoff a little bit, but think about it's a log scale. So we're actually looking at quite a bit of evolution between now and redshift 0.3. So what do we find? So MAGPIE, by design, targeted a representative range of morphologies and environments. And what we see, indeed, when we look at the visual classification of galaxies is that, indeed, we find the range of morphologies that are already in place at redshift 0.3 that we see today at redshift 0. In this plot, in the central plot, I am overlapping as tiny squares. In the background is a local survey, IFS survey equivalent, the SAMI survey with the same color scheme for the morphologies in the spin ellipticity diagram. I suspect we'll see that diagram a lot in the next couple of days. And then you can see the MAGPIE equivalent in the big circles, not because it's bigger and more important, but because it would be completely drowned if I use the same size symbols as SAMI, because there are much fewer galaxies. And so you can see that the morphological, this is not news, okay, but we are selecting a representative sample in morphologies. Now, if I go to the right-hand side, now what we've done is a visual classification of the kinematic maps, so in this case, the stellar kinematic maps, and people have voted whether they saw rotation or not. And the galaxies that don't show rotation tend to be obviously in the lower part of this plot. Now, everybody's eyes went to the little black dot at the top. This is a galaxy where it changes. It rotates in the center and not in the outskirts. And so depending on who voted what, it ends up preferring non-obvious rotation in this case, okay? But it's not a bizarre outlier. It's just that it has this change of modulation. Okay, so we are finding that at redshift 0.3, the non-rotators or the slow rotators are already in place. They are established, right? So we heard from Sedona that all galaxies at high redshift are disk-like, and I'm going to say that not all galaxies at redshift 0.3 are disk-like, or at least rotate like a normal disk. We have in place already a population of non-rotating galaxies. Okay, so this is a very busy plot, and I'm gonna really focus on the one that's got a big bright red rectangle around it. What I've done is that it's a small sample compared to some of the tens of thousands we heard about, but I've divided my sample into two bins, basically at the median, so that I have roughly equal numbers. And what you can think of in this plot is that each of those bars are essentially pie charts. So it shows you the fraction or the ratio of like obvious rotators to non-obvious rotators as a function of environment. So low environment to the left, high density environment to the right, in this case, coded with group mass. And so it looks like at redshift 0.3, the non-rotating galaxies do not prefer denser environments. I'm sure there'll be lots of questions about this. Okay, how else can we look at the potential impact of environment on the dynamics of galaxies? I see lots of furrowed brows. I love it. Okay, that was my reaction to what have I done wrong? Anyway, okay. So this is work by Francesco Eugenio, and so he's using the higher order kinematic moments, the Gauss-Hermite decomposition of the line of sight velocity distribution. The fourth moment is H4. This is essentially a measure of the number of stars in the line of sight velocity distribution that are in the wings. So the more stars on these hot orbits in the wings of the line of sight velocity distribution, the higher the H4. Okay, and so he's looking at this central H4, which you measure on an integrated spectrum in the center of these galaxies, comparing legacy at redshift 0.8, so not yet high redshift, but okay, we're getting there, and to the local survey, and then MAGPIE in the middle, and we can see there is an evolution, right? So H4, whatever it encodes, evolves with redshift. Now, this has been interpreted as potentially being an indication of the number of dry mergers that have added, minor dry mergers adding hot orbits to the line of sight velocity distribution in these galaxies. And so we think, or we've interpreted, and I would love to hear other possible interpretation of what this H4 might mean, but perhaps it is an indicator of the number or cumulative dry minor mergers across time. right? So things today have experienced more minor merging. Makes sense. Okay, so thank you. If I use this, and so this is work that's in progress, and I'm using this H4 again, and I'm color coding my points as a function of H4, and we saw that environment maybe matters, mass matters, age matters. I'm also throwing in there the mu SFH in this case is the peak or the predicted peak of the star formation history for these galaxies. And you can see that in this case, even with the partial correlations when I account for all the parameters, which is what the arrows are showing, I do see a significant trend with environment. Okay, so this H4 parameters still cares about environment as well as age, unlike spin parameter. So it's a slightly more sensitive parameter to environment, which again gels with our story of minor merging being more prevalent. But if I separate my galaxies in satellites and centrals, suddenly this dependence on environment disappears for central galaxies. All that matters to them really is how old they are, which in my interpretation may be naive, and I would love to hear about this, is when did their dark matter halo collapse and form the majority of their stars? That is what matters for what sets how these galaxies' dynamics behave today, right? So maybe it's not something that happens over time. For these central galaxies, they don't really care about the environment anymore. They dominate it. And so next, I have some work by Ryan Bagg, who's in the audience here at the back. So if you've got questions, please also have a look at his poster. He presented it earlier, but it's still available online through the QR code. Ryan is using kinemetry to measure the kinematic asymmetries, so departures from normal rotation in the stars and the gas. So in this case, I'm showing the stars. And so as a function of stellar mass, we can see that in MAGPIE at higher redshift, there was higher kinematic asymmetries. Now, these kinematic asymmetries in the stars, at least, have been interpreted as signatures of recent major or intermediate merger events. So these galaxies in the past at redshift 0.3 seems to have been, for the same stellar mass, experiencing more mergers or disruptive, something that disrupts the kinematics or their nicely rotating disks. And finally, I would like to also showcase some work by Gary. So she's been using 3D Barolo to measure the rotation curves, so doing some of the similar stuff to what Sedona was showing, taking into account some of the observational effects. And so she's able to measure the dark matter fraction. In this case, I'm showing for the dark matter fraction in the outer regions. And so basically, she's seeing that there's a trend with stellar mass, and then she's also trying to tease out using the same methodology for all of the surveys. This is ionized gas, to try and look for evolution in the dark matter fraction. So I'll let people debate, and I'll defer all questions to Gary. And so finally, I would like to also highlight that there are other tracers of dark matter, and there are other ways that we can try and tease out the assembly history of galaxies. And one of those is to look at globular clusters. Okay, globular clusters extend outside, way out in the halo, so they're a great probe. So Sadaf, who is sitting here in the front, has a poster about this. Please scan the QR code and have a look. This is going to be the largest sample of extragalactic globular clusters around spiral galaxies. So we're very excited about this PhD project. There are many other papers I couldn't present. Richard McDermott is going to present soon as well. There's 13 publications, one of those not included there because it just came on the archive. So please look us up, have a look at the MAGPIE survey. We're very excited about the science that's coming out of it and what it's telling us about galaxy transformation when we look at it as it happens. I'll leave you here with my final thoughts. Thank you.
Questions? So, yes.
Thank you. Thanks for the nice talk. I was trying to understand how exactly you measure the H4 parameter, and if you have a good sense of what are the real uncertainties associated with it, because I know that at redshift 0 with arguably even better, this is a beautiful data, but like redshift 0, there are data sets with even higher quality. It's extremely hard to measure it and to disentangle this high order parameters with respect to the overall motion of the disks. So I'm trying to understand if you have benchmarked this to redshift 0 galaxies, and also, what are the uncertainties in this
So
H4 parameter?
your question's about age and H4. Yep. So one of the things I didn't mention is that the resolution, at least the spatial resolution, is very well matched to some of those local surveys, like the SAMI and Manga surveys, for example. So because we have MUSE, because we have AO, we're actually able to have a very comparable sample. So that shouldn't be at play, but of course we should always be careful. In terms of the age, we're using full spectral fitting with PPXF, the usual shebang. We've got very good, we go out in some galaxies to 2 and a bit effective radii. So like we're looking at a similar to what you get locally, but obviously we have less because then it would cost us too much to stare at those for that long. So it's a really beautifully rich data set. And the ages you can trust as much as you can trust them locally.
Thank you.
Yep.
Okay, we don't have time for another question. So if you have one, put it on Slack or on the Zoom. Thank you. Thank you. Can we change the slides? Can we change the slides? Okay. So next we have Lilian Lilly from Max Planck Institute of Garching in Germany, and she will talk about the crystal surveys resolving the kinematics of typical main sequence star-forming galaxies at redshift 4 and 6. Very interesting. Probably it's a language problem. It's short in 5 minutes. Thank you. Here you go.
Good morning, everyone. My name is Lilian Lee. I'm a PhD student from the Max Planck Institute for Extraterrestrial Physics in Germany. And thank you very much for this opportunity for giving a talk here. So today I would like to tell you more about this crystal survey, which is an ALMA large program targeting star-forming galaxies of redshift 4 to 6. So in the next 12 minutes, I will be focusing more on the kinematics properties of the sample. But before that, let us step back a little bit in time and redshift to appreciate the efforts spent by the ground-based IFU survey over the past 2 decades, which have taught us a lot of important things about dynamical evolutions for galaxies at cosmic noon, an epoch that is the peak of cosmic star formation and is responsible for forming most of the stars that we see today. And thanks to those IFU survey, it is now very well established that those galaxies at cosmic noon are predominantly disks. However, these disks are not quite like our local massive disk, because when we look at them through the ionized gas tracer, we see there is an increasing trend in their gas velocity dispersions, as well as a decreasing rotational support relative to turbulence, as reflected by the decreasing ratios between the of the V over sigma as we go to higher redshift. The colder molecular gas tracer tells very similar stories, and these trends can be explained reasonably well by the tumor theory, which says that a disk will be more gravitationally unstable if it is gas-rich, which is indeed typically the case as we go to higher redshifts. So before I venture into the even higher redshift universe with ALMA data, I would like to first give you the reference value that we would expect for this ratio, V over sigma, for, say, a typical local massive disk, then this will be around 10. If this ratio shoots below 1, then it is a valley rotation supported system and is believed to be more common as we go to higher redshift. So now, here are the C2 measurements based on the ALMA data. However, despite the considerable effort spent to gather a sample suitable for kinematic study, the samples still remain very limited and resulting in a heterogeneous set of data, with each data set probing quite different galaxy populations with very different physical processes regulating their evolution. And among this heterogeneous set of data, there are some measurements suggesting that these high redshift systems behave just like local massive disk with V over sigma reaching 10. So how crystal could contribute to this picture is to then offer a more homogeneous selected set of galaxies that would be representative of the galaxy population at these redshifts, with the star formation rate surface density and the baryonic surface mass density situating in the shading of the plots that are on your right, hence capturing the bulk of the populations like the HLVer and CO study did for lower redshifts. In other words, Crystal offers an improved resolution and a deeper view of typical galaxies at redshift 4 to 6. Or you can understand them as they are all main sequence galaxies. So here I overlay the JWST and HST images of the crystal galaxies, as well as those lying within the field of view, but we analyze them anyway, on their Spiegel's relations. So on the first look of these images, they appear very irregular and clumpy, look like those disk galaxies observed with HST years ago. And the lessons we learned back then is that because the HST could only see the rest frame UV of the cosmic neutron disks, hence preferentially capturing the bright star frame clumps in those systems, and you would underestimate your true disk fractions by interpreting those clumps as merger galaxies. So now we are seeing a very similar problem with JWST for galaxies at even higher redshift, because it could at best override the rest frame optical view of these sources. So the lesson we learned back then is that the kinematics will still remain a more reliable tool to discern truly the dynamical state of these systems. So here are the velocity views of the same set of galaxies that we extracted from the ALMA data. So despite the clumpy and irregular look in the previous slide, now an overwhelming majority of them have a coherent velocity gradients. And of these velocity gradients, some of them can be explained nicely by the disk rotation model, which I will go into details later. And in some of the few cases, we see a evidence of outflow, which is already visible in the integrated spectrum of the C2. However, with the current data quality, we are yet to conclusively tell the origin of perturbations for the remaining of the sample, whether the origin of perturbations is coming from galaxy-galaxy interactions or merger-triggered instability, or yet unresolved inflow or outflow motion of the gas. However, one thing we know for sure is that if these systems are mergers, then it is more challenging for us to study the dynamical states of these systems because we simply cannot model them as disk anymore. So in the remaining of my talk, I would focus more on the disk sample of crystal. But before that, we need to devise a scheme to classify which of these systems could be disk candidates. To do that, we've explored a variety of methods that have existed for a while and had proven to be quite effective for lower redshift, higher quality data, including the kinemetry, which can quantify the 2D, the asymmetry seen in the 2D velocity and dispersion maps, as well as a technique that we borrowed called spectrophotometry, which can help revealing more subtle velocity gradients that are sometimes not quite resolved by your angular resolution, but this method cannot lead you to very far out of the galaxy by design. These two quantitative methods are then complemented by visual inspection of the rest frame optical to UV images of these galaxies, as well as the conventional PV diagram and the V/2 sigma, which simply is the ratios between the peak-to-peak velocity difference divided by 2 times the integrated line width of the C2 emission. So all of the galaxies in crystal went through these classification methods, and overall, we found that the galaxies broadly fall into these 3 big groups. The first group would be the disks that are as good as you can find at these redshifts. They have a monotonic velocity gradient and a centralized dispersion peak, peaking at where your gradient is the steepest. There are also no visible companions in sight in all of the wavelengths available to us. The second type of disk, they are still disks that don't pass all the check boxes. They are usually located in systems with multiple components. For example, the one here, the bigger one here is not a disk. However, the smaller one in the yellow orange circles exhibits some compelling evidence suggesting of disk rotations. The last type would be those systems that cannot be classified into the first 2 groups. We don't know what they are exactly, but they do not have a well-defined velocity gradient or a dispersion peak. And overall, we found that just about half of the samples fall into the first two groups. And this number of these fractions, interestingly, is consistent with some of the morphological studies based on JWST imaging data alone. So now, having the knowledge of which of these systems are disk, we can then proceed to kinematics modeling to then extract the intrinsic velocity and the velocity dispersions of these galaxies, accounting for the observational effects. To do that, I first extract the velocity and dispersion profiles from the original data cubes. And then with these two profiles in hand, you can then ask the questions of what kind of mass distribution can give rise to these rotation and dispersion. And this is exactly what our DismoPy, as the donor has advertised, is for. In case you miss it, in short, DismoPy is a full 3D forward modeling tools that starts with a series of parametric mass model, comprises of a dark matter halo, a baryonic disk, and bulge, etc. The users can flexibly tune the relative contribution of these various components. This intrinsic model cube will then conform to the same spatial and spectral resolution as your data and compare the model profile to your data profile in exactly the same way. So with DismoPy, here is the best fit model of these particular galaxies overlaying the black stack lines in the upper panels and the red squares in the new panel. The mass components as well as the dark matter fractions that this model carries can be easily extracted from the intrinsic circular velocity curves, as well as the intrinsic dispersions accounting for the beam smearing and other observational effects. So for these particular galaxies, the velocity dispersion is about 60 kilometers per second, and on average for other disk galaxies is about 80 kilometers per second for the velocity dispersion. In other words, they are quite turbulent disks for galaxies at this redshift. If we were to compare the crystal values with the literature values that I showed at the beginning, which is a reminder, the H-alpha and CO studies mostly for lower redshift and the C2 measurements for redshift about beyond 4. Crystals values lie in these parameter space that is consistent with what the tumor theory predicts for galaxies at these redshifts. And then the next thing we investigate is the dark matter fractions. However, with the current state of depth, we are still limited to observe the very outer parts of the rotation curves on a very large halo scale because we hardly have any constraints there. Nevertheless, on galactic scale, the crystal galaxies tend to be quite baryon dominated with a median dark matter fraction of 14%, although there is a wide range of values among the sample. So follow-up study with deeper and higher resolutions observations would definitely be beneficial to how reducing the uncertainties of individual measurement as well as to discern which of these possible mechanisms is the most responsible for depriving the galactic scale of dark matter. Also to give us a better handle on the shapes of the outer curves of the on the outer parts of the rotation curves. It's nevertheless interesting to see that the crystal values overall lies on this line that is extrapolated from the relation based on the RC100 study, as the donor has highlighted, which is the collections of the best quality of rotation curves for galaxies as cosmic Newton. And I believe it is perhaps time for me to summarize, so I will leave you here with my summary slides. Thank you.
Anybody else has question? Otherwise, I'm going to give the chance to Pavel again. Okay, so Pavel.
Thanks for that. I'm trying to understand how this kinematic modeling software works, and in particular, the data that you were showing is barely resolved. So clearly, the disks don't extend more than 1 or 2 beams, but yet the rotation curves that you show have many more elements. I wanted to understand what does that mean? And also I noticed that the rotation curves are asymmetric. I also want to understand where that's coming from.
Thank you for the question. I think we've met before in the summer school, if you remember. So unfortunately, my slides are gone, but then the example that I'm showing, that's the galaxy is actually resolved by more than 3 beams. And if you take it on medians, and it's also true for most galaxies in the sample, it is resolved by at least 3 beams on one side, which means you have 6 beams for that particular galaxy on both sides. And in the, okay, I can actually go to the slide to show you. So if you pay close attention, the data profiles.
Yeah, for example, there is like one beam, right?
Yes, that's the worst case will be covered by only 3 beams across the whole galaxies on both sides. But these galaxies is the typical of the better sample we have. So the great data points with error bars in the lower panels are actually flipped. The negative rotation side to the positives. So you see they match very well with the data, which means they're quite symmetric on both sides. Because I flipped the negative side to overlay on the positive side to see how symmetric they are. So, and it's also true for other cases then we find quite symmetric rotation curves, but it's true that there are some examples, for example, the, if I can go back, because we have 2 classifications of this. So for the second type of this, yes, you will see they are not quite symmetric on both sides.
Okay, thank you. If I am allowed to super quickly, just going back then to the first question in this example you were showing, like if you go back to the next slide. So I'm just trying to understand, how do you end up, for example, in this case, that is 1 beam, you end up with 4 or 5 points in the rotation curves. I'm just trying to understand how robust is that, how much can be.
We do some super sampling of the beams, which is the typical practices in this case. Then you can better gauge the shapes of the rotation curves, but we do some super sampling. As you can see, this line here is the Fourier half measurement of the beam. So we did a super sampling of a factor of 3 in this case.
Thank you.
2D first, quick difference of looking at the 2D extraction versus what we're doing in 1D. We were looking at basically flared pseudo slit to try to tease out the lower signal to noise, where the 2D representation here is we're losing signal out there, but you can tease out a bit further in that pseudo slit too. So that's why we, trying to push a bit further than what we're representing here in the 2D map.
Okay, thank you, Lillian. Let's thank Lillian again. Can we have slides from next one? So our next speaker is Taimur Saifulli from Observatory of Strasbourg, and he will talk about weighing dark matter using dwarf galaxies. So now you should notice that we are changing the tracers for dark matter. Earlier we were talking about the galaxy, and now we are talking about dwarf galaxies. So yeah. Taimur.
Thank you very much. Good morning, everyone. Before seeing my presentation, one thing I want to mention here is that when I wrote the abstract for this talk about 6-7 months ago, I had a different plan in mind. And since then, lots of things has happened. And I talked to lots of people and collaborators. So overall, what I'm presenting is what I intended to present. Some results might be different. And also what I'm presenting is what us as the community of dwarf galaxies and other things about dwarf galaxies I will mention, we're going to do. So it's not just me, but it's a work that the community will do. And so today I'm going to tell you about maybe a secondary approach to measure the mass within galaxies, the total mass, and let's say if it's dominated by dark matter, it's dark matter mass. It is very beneficial, especially for dwarf galaxies, for low mass galaxies, objects that we are studying for years. Objects like, if it works, yes, like NGC 6822, a local group dwarf galaxy, and many more in the local group around the Milky Way and Andromeda galaxy, that actually most of the information that we have about dwarf galaxies, about their mass, comes from these objects, the nearby ones. And something that is settled is that these objects are quite dark matter dominated. Looking at these plots, on the x-axis, you see the absolute magnitude of these galaxies. Let's say it's a proxy for stellar mass. And on the left, the objects become fainter and fainter, but then they go up on the y-axis, which represents the ratio between halo mass to stellar mass. So they become more and more dark matter dominated. This is something we know. And also this motivates lots of people to study these objects to maybe find some hints of the physics of dark matter on the side of studying the baryonic physics, right? And then what people find are these tensions and inconsistencies between observations. Here I'm showing this very nice portrait table from a very recent review. Some authors in the audience. And if you look at the list, you will recognize some of these inconsistencies. Some are discussed for years, but also there are uncertainties. Like what I'm going to talk about mostly is the uncertainty that we have about stellar to halo mass ratio of dwarf galaxies. So, in my opinion, these are mostly based on local group, but also measuring mass in general is hard. So you need to have more and more galaxies observed. We have tons of dwarf galaxies in galaxy clusters, for example. There are a bunch of them, of these nearby galaxy clusters that we can observe and find global clusters, measure the masses. But overall, it's not an easy task. And that's the whole point. It's not easy to measure these masses. That's why there's uncertainty. And that's why we are trying to do something a bit different than before. So as the result of these uncertainties in stellar to halo mass ratio, we also have differences between models that predict the stellar to halo mass ratio of different halo masses. I think this plot will be shown more and more in this today and on Thursday. You see the curve, the peak is something that represents Milky Way-like galaxy. And on the left side, you start to see the galaxies that are less massive, like the regime of dwarf galaxies. And you see that all these lines are of different models that are plotted start to become a bit different from each other. So that's because uncertainties are there. And once uncertainties are there for observations, and models cannot really try like a constrained. So that's the issue, I guess. And so we need to measure masses. There are a bunch of different ways to measure mass. We heard about them, and we will hear about them more. I just put here some of them. I also name some of my friends, but there are more people doing this kind of things, definitely. But look at them. All of them are great, but each of them have some sort of limitation. Look at the stellar dynamics, stellar kinematics. Dwarf galaxies, when they start to become low surface brightness, it's very hard to observe and get proper signal-to-noise ratio to get kinematics and measure masses properly. Global clusters. Not every dwarf galaxy has global clusters. And if they have a few. And can we measure some mass based on a few global clusters, yes or no? Well, there are talks about that. But also there's H1 kinematics, which is a proven way to measure mass, but then you need to have gas at the first place, right? So all of these are good, but overall, every method has its own limitation. So what I'm going to tell you about it is about global clusters, but not by kinematics, just by looking at images and counting how many global clusters are there around these galaxies, around these dwarf galaxies. So this is motivated by a scaling relation, was known for years for more massive galaxies, that more massive galaxies have more global clusters. Okay, and I must say maybe 5 years ago, it was a bit uncertain if it works for dwarf galaxies, but now data is collected, and we also see that this would work for dwarf galaxies, but it doesn't really work for one dwarf galaxy. That's the thing. It works for the population. On average, we expect that this relation work, but it doesn't work for one dwarf galaxy. You cannot measure one mass of one dwarf galaxy, but you can apparently you can trust the average behavior. Because every galaxy goes through something different. Look at all these dwarf galaxies showing here. All these points on top of them, well, some are just random stuff, right? They can be foreground stars, background galaxies, but some also the global clusters. And the task that we have, at least my side of the observational side, is to understand, to identify which objects are global clusters. So that's the task here, and that's what we are trying to do. You have a dwarf galaxy, you want to find out, you have deep images, you want to figure out what is a global cluster around this galaxy. If you have unlimited time and money and telescope, you do a spectroscopy for everything, you figure out, okay? But no. So what people do deep imaging and trying the best analysis to measure sizes and colors to make some sort of selection based on photometry. And it works, but when galaxies start to become more distant, then it starts to become tricky because these global clusters start to be very small. And also seeing limited data of ground-based observation makes it hard to measure the sizes properly. Then, just looking at this, we go to space. With HSC, we have the special resolution that can help us to even go further and further and measure sizes properly. But the problem with HSC is that I don't know how many galaxies you can observe with HSC. Are always limited to kind of program you want to make it through the TAC and what kind of science you want to do. It's not possible to make it for a large sample. So that's where we stand now. And now, thanks to Euclid, we have something like the HST in space working already. And in the next 6 years, it's going to image about 1/3 of the extragalactic, 1/3 of the whole sky, which is the whole extragalactic sky, in the resolution that is comparable to the HST. So that's perfect for things like global cluster identification, right? And despite this special resolution, again, it covers a large fraction of sky. And rough estimation would tell us we will observe around 10 or even more thousand dwarf galaxies over these 6 years. So there is a lot of dwarf galaxies to be observed and analyzed in terms of global clusters. So that's the kind of sample I'm talking about, right? Euclid will come, well, the data will come. Now we have access to early release observations. Maybe you've seen these images before. 10 of them were released by ESA. There are more observations, and 2 of them in particular, Fornax galaxy cluster and also Perseus galaxy cluster at different distances. These are the ideal data that we can explore and see what we can find in terms of global cluster and how global cluster identification works for these different distances. So for something like Fornax, this is a dwarf galaxy view you see a fluffy component, like the stellar component of the galaxy. You see the nuclear star cluster. You see all these points around it. You see how much resolution it brings compared to Dark Energy survey. And then, yeah, we know some of these around this galaxy might be global clusters. We do our analysis based on measurement of sizes. And for this distance, we actually can resolve. We can see that some of these points are not PSF. So they are resolved. They could be global cluster. And if they satisfy some color criteria, then we can call them global cluster candidates. We do this kind of things. For Perseus, it's more distant. Objects these global clusters are not resolved. But then, for example, in this case, we realize that for that particular direction of sky, the colors of these global clusters does not really overlap minimally with the colors of stars that are in the foreground. So every object, every galaxy cluster, or every, let's say, dwarf galaxy given distance and location can be a bit different, but overall we're trying to do something uniform. Because the main thing is that this relation exists, but there are also a lot of uncertainties around it. There are lots of uncertainties around counting number of global clusters. As we will see in the community, different people count just for a given galaxy. We count them, we do analysis, and things are different. 5 minutes? Wow. Okay. So let's take my time a bit. So, yes, yeah. Okay. So, yeah. So this plot, X, Y, there are 2 axes, 2 main sources of uncertainty. One is the number of global clusters on Y-axis. This is the part that I'm responsible for. And again, I was always saying that we have some sort of inconsistency between different groups, counting number of global clusters. And to me, it seems that it is not because people do different methods, it's because people assume different things. You cannot just look at images and count them. There are some assumptions about how many global clusters you don't see in your images, how many of them are further from the galaxy, and there are corrections. And these corrections are based on some previous knowledge that apparently it's not exactly right for every galaxy. So for every galaxy, things can be different. So this also adds to uncertainties and errors that we might get from number of global clusters. So it's a quite of a task to deal with. Also on the other side is the uncertainty, the mass measurement. In these plots, in this scaling relation, actually a significant amount of scatter comes from different tracers that have been used for mass, and different tracers will give you different things slightly, right? So this adds to the scatter, and maybe for us as community, we need to look for objects of maybe certain type of morphology and look at global cluster in a certain way, try to measure the mass in a certain way that can be comparable. And then after having all these, we can possibly recalibrate this relation. And once this relation is recalibrated, then we can apply to all these dwarf galaxies that has been observed. So that's the whole idea. And I have more time, right? Okay, I don't need more time. I'm really happy that I could present this approach to you because I think we need more and more attention. You don't need to do it, we'll do it, but it's that there is this secondary approach to maybe constrain the stellar to halo mass ratio of dwarf galaxies. So that's the main message here. And I hope also could fascinate you by all these images of Euclid, early observation. And at the end, I'll be happy to answer any questions. Okay.
Yeah, we have one question back there.
That too.
Hey, thanks for the talk. Eric Tollard, Space Telescope Science Institute.
Hi.
I'm curious whether you thought about the Roman Space Telescope, and whether any of its proposed surveys are going to be complementary, better or worse in some way to what you're talking about.
Yeah, I'm not aware of the depth of, for example, let's say the high latitude, low latitude. I don't know names of these fields that Roman's going. So, but my impression is that it's deeper. So, I mean, Euclid is great, but Roman is deeper. So we can really, for example, constrain the whole shape of the luminosity function of global cluster around these dwarfs. And that indeed is a whole different science case. Yes.
Have you thought of, sorry, Connor Bottrell, ICRAR, have you thought about right here.
There.
Oh.
So have you thought about how much intrinsic scatter you might expect in this relation between the number of globular clusters and the dynamical mass? Because you've talked about some two observational sources of scatter. Yeah.
Like physics.
I mean, so like whether the globular clusters are actually virialized within the halo and are therefore actually really dynamical tracers of the halo.
So, I mean, dynamical tracer is the different.
Just by their number.
Yeah, okay. I see. Okay. So that's quite of an unknown territory, to be honest, that how much this number can really scatter based on the physics. I mean, it's reasonable that every galaxy went through different process, and some may lose global clusters, some interact, the dark matter will go away. So things can happen, and I don't know, I don't have an answer for that at the moment. But it will be huge. Like we have a large scatter in the mass of dwarf galaxies anyways. I expect the same for global clusters.
We have a question back there.
Thank you. Very nice talk on HED, University of Chicago. I have a very naive question. I might have missed this, but are the number of globular clusters a tighter tracer of the stellar mass or a tighter tracer of the halo mass?
So once again, if global clusters are what kind of tracers of?
Stellar mass or than the halo mass, or do they trace the halo?
So the relation is about halo mass.
Okay.
Yes.
But do they also trace the stellar mass tightly?
But it's not, I mean, I would say not like this. I mean, there's this correlation between, you will see some correlation, but it's not like a correlation similar to this. It will be more complicated. Depends on star formation history and stuff.
Okay, let's thank Sergio again. Next, we have Luisa Bozo from Swinburne University, and she will talk about a comprehensive view of luminous and dark matter of ultra-diffuse galaxies.
Okay. Hey, everyone. While they're loading, I'm Luisa Bozo. I'm a PhD candidate at Swinburne University in Australia and at IAU in Germany. And today I'm going to talk a little bit about my PhD thesis, which is focused on the luminous and a little bit about the dark matter content of ultra-diffuse galaxies. So just to start by setting up the stage, ultra-diffuse galaxies, in a nutshell, they got very popular in 2015 when they were found by the dozens in the Coma cluster. And the interesting thing about them is that they have the luminosities of dwarfs, but the sizes of giants. So here, no, that's fine. Here's an image to scale of an ultra-diffuse galaxy. And you can see that, well, you can barely see it. And that's because its luminosity is similar to this dwarf elliptical galaxy here shown for comparison. But it's very extended, having an effective radius similar to that of the Andromeda galaxy. So only by looking at this image, we can already start to think on ways these galaxies could be formed. They could have come from dwarf galaxies that got through some internal process that was able to enlarge them. And this is what we call a puffy dwarf formation scenario. Or they could have started their lifetimes as giant galaxies being hosted by giant-like dark matter halos, but something happened early on that halted star formation. That halted star formation, so they didn't form enough stars and they didn't become what they were supposed to be. And this is what we call a failed galaxy formation scenario. Now, in terms of observational properties, we know nowadays that UDGs can be found in all environments. They have a variety of cell populations, a variety of morphologies, but what is most interesting about them, and this traces back to what Taimur was talking about, is that they can host surprisingly numerous globular cluster systems, or none at all. So here are 3 examples of ultra-diffuse galaxies across different environments, and what they have in common is that all of them are globular cluster rich. And this is just to show that the environment that the galaxies reside in is not necessarily correlated with their globular cluster richness. So, okay, we know of some observational properties, we know of some formation scenarios, but how do we make this correlation? How do we find signatures in these properties of these galaxies that could allow us to trace back their formation scenarios or to have any hints on their formation scenarios? And this is exactly where my PhD thesis comes in. Our idea was to try to put together a large sample of galaxies using photometry to understand a lot of their properties and to maybe try to correlate this with formation scenarios. So this dates back to 2022, when we started looking at these galaxies and making correlations from their cell populations on globular cluster richness and environment. So here I'm showing the age metallicity plane, and all of the UDGs are overlaid here, color-coded by the environment that they reside in. So in green are UDGs in the field, and you can see that they are systematically younger than their cluster counterparts shown in pink. On the other hand, if we look at the exact same data distribution, but now color-coded by the globular cluster richness of the galaxies, what we see is that globular cluster poor UDGs, shown here in blue, they are systematically more meta-rich than their globular cluster rich counterparts. And this is very interesting, very unique that we saw for these galaxies, and we decided to really explore why they were so different. And so we did this by looking at the mass metallicity relation, which can give us clues on how these galaxies were formed. So just for some context, this is the mass metallicity plane, and we can use it to compare this to well-known galaxies, well-known mass metallicity relations, to try and find where these UDGs lie in. So here are 2 of our samples in red and in pink for different types of UDGs. And for comparison, we have here in green the sample from Lana Fermató, which is completely focused on spectroscopy. And what we can see is that regardless of the mass range that we're looking at, UDGs always split into 2 kinds. One mode that is perfectly explained by the mass metallicity relation for classical dwarf galaxies, which is this one up here, and another mode which is better explained by this other mass metallicity relation, which is based in simulations, and it's for galaxies at high redshift, which is indicative of early quenching. But what are the differences between these 2 types of UDGs? What can we talk about their observational properties? So we looked into many different properties of them and how different they are. So let's first focus on the UDGs that perfectly follow the mass metallicity relation for classical dwarf galaxies. What we have found is that they are systematically fainter, smaller, they are more elongated, they live in the most isolated environments, they are younger, they have very prolonged star formation histories, they have a very small number of globular clusters or none at all, and they have on average smaller GC-specific frequencies. If we look at the UDGs that follow the mass metallicity relation that is indicative of early quenching, they show the exact opposite trend. I think this is easier to see in this plot here, but what we've done was basically to put all of the information that we had into the multi-parameter space and applying a clustering algorithm to try and find classes of ultra-diffuse galaxies. And what we have found is that 2 classes best explain our sample of galaxies. We have class A here in green, which is exactly the one that I mentioned before that perfectly follows the classical dwarf mass metallicity relation. But we have another one that is class B here, that its properties are that the galaxies are much more massive, they are redder, brighter, they have much larger mass to light ratios, they are older, they have very quick, very short star formation histories, they are rounder, bigger, they lie low in the mass metallicity plane, and they are better explained by this early quenching scenario. They have very large numbers of globular clusters, very large GC-specific frequencies, and a larger GC mass normalized by the stellar mass of the galaxy. These galaxies, they have a very large number of globular clusters, and because of that, exactly because of what Taimur was saying, we believe that they are hosted by this larger, overly massive dark matter halos. So because of this, we associate galaxies in class B with having this failed galaxy formation scenario. So being hosted, having a giant-like origin. On the other hand, galaxies in class A, they have properties similar to dwarf galaxies in general, so we believe that they are likely puffy dwarfs. What is interesting here is that the number of globular clusters seems to really drive this separation. So the number of globular clusters is very important to understand these galaxies. And then if we look at another type of galaxy that also have weird globular clusters, we go back to the NGC 1052 group, which, if you're familiar, is a very controversial one because it was proposed to host some dark matter-free galaxies, DF2 and DF4. And what is unusual about these galaxies is that they are dark matter deficient, if you believe that, but they also have very unusual globular clusters, more massive than usual. So they have a top-heavy globular cluster luminosity function. And many works have tried to explain both the dark matter deficiency of the galaxies and the unusual GCLF. But one of the works that have tried to do this is this bullet dwarf collision, where the basic idea is to be a mini bullet cluster. So the idea here is that two galaxies collided at high redshift. And so dark matter and stars that are collisionless, they just pass through, but the gas that is collisional collides, forming a lot of new stars and a lot of massive globular clusters because of this high pressure of the high-speed collision. And then these galaxies end up dark matter deficient and with globular clusters more massive than usual. The problem is this scenario was proposed to happen 8 times every 20 megaparsecs, but apparently, so far we just know of the galaxies in the 1052 group. And so we found this new galaxy. This is FCC 224, FCC 224, which is a galaxy in the outskirts of the Fornax cluster. And we have 2 works working on it now. This is from Yimeng Tan from UC Santa Cruz. And what he's doing is studying the HST data. And he has found that the galaxy has 13 globular clusters. And this is the GCLF of FCC 224. And you can see that it's also top heavy compared to DF2 and DF4. And it's much brighter, at least 1.5 magnitudes brighter than the regular GCLF for normal dwarf galaxies. Then we decided to follow this up with KCWI. This is the work that I'm currently working on. And our idea here was to try and confirm the association of the globular clusters and the dark matter deficiency of the galaxy, if it is dark matter deficient indeed. So with this, we were able to confirm association of 6 globular clusters, and one of them in the field was found to be a foreground star. And again, this here is in gray, the proposed GCLF of FCC 224 by Tang et al. And these are the 6 globular clusters that we confirmed, confirming the top-heavy GCLF of the galaxy. So now we really need to probe its dark matter content. And so we did this by using both the red side data, which is very high resolution from KCWI, and MCMC on the globular clusters that we were able to confirm. And both of these measurements have shown, 7.5 kilometers per second for the velocity dispersion and 5, which are both indicative of no dynamical evidence of dark matter in the galaxy. If we look into this in this plot here, we have what is expected for if the motions of the galaxy are completely driven by stars, this would be between 4 and 11 kilometers per second. And if the galaxy had a normal halo, it would have more than 29 kilometers per second of velocity dispersion. And what we see is that both the globular cluster measurement and the star measurement put the galaxy in this region without dark matter. Again, if we look at this in terms of dynamical mass and stellar mass within one effective radius, we see that these galaxies that follow the 1-to-1 line, meaning that they have a dark matter fraction consistent with 0, which is similar to DF2 and DF4 and other galaxies that were found to be dark matter poor and very different from other quiescent ultra-diffuse galaxies studied in the literature. So just to finalize, just to mention that we are going through this in much deeper data. We recently got 17 hours of Muse data to really go through all of these globular cluster systems and the dark matter deficiency of the galaxy to really probe it further. So now just to finalize, this was the first statistical study of all the properties of UDGs. And we were really able to show that the globular cluster system is key to understanding the different properties of UDGs. And then here, I give more of a rule of thumb, more than anything set in stone, that if UDGs have a regular GCLF, we can separate them in, if they have regular globular cluster numbers for their stellar masses, they are likely puffy dwarfs. If they have more globular cluster than is expected, they are likely failed galaxies. But then if we're talking about irregular GCLFs, which could be that they have irregular dark matter contents, then we could be talking about some more exotic formation scenarios, something like bullet dwarfs or maybe tidal dwarf galaxies. And that's it. Thank you.
Yes.
Thank you and great talk. I'm very curious about how a galaxy could be so prolific at making very massive globular clusters, but not stars.
I think it has a lot of stars. It just doesn't have dark matter. So, but wait. Like here, it has a lot of stars. The thing is that the stellar content is more diffuse. But the stellar mass of the galaxy is similar to a regular dwarf galaxy.
So it doesn't have more globular cluster for its mass.
These type of galaxies, no, they have around 15 globular clusters. The thing is that these globular clusters, they are more massive than expected. So they are at the high end of the GCLF.
Great.
We can talk about it. Yeah.
Hi, really interesting talk. I'm just curious, are there any UDGs near FCC 224?
There is. There is one that we really want to follow up. This is FCC 240. It's very close by. It has exactly the same PA, the same ellipticity, and it seems to have also bright globular clusters. So we could be seeing a twin of the DF2, DF4 group, which would be really, really interesting.
So there is one question online from Soudmore. Is it correct that the FC 224 system is a satellite galaxy? And if so, is it correct to consider the Moster et al. Relation, since satellite galaxies are affected by all sorts of tidal effects? So it's about the environment of this galaxy, I guess.
Well, we're not really sure about the environment of the galaxy. So it is at the outskirts of the Fornax cluster, but we are still trying to understand if the galaxy is within a group that is infalling the Fornax cluster, or if the galaxy is more isolated. So I don't think we have any information so far to say that it's a satellite or not.
Okay, thank you. Thanks again, Marisha. So now we had two lightning talks, and they're given by two of the geniuses in the field. And that's why they got probably the lightning talk, because you guys can go to them and talk with them. So I will ask them to put the slides on, and I'll ask Enrico and Michael to come here, and we'll have three minutes of presentation. You can ask question probably in the end from both of them. Yeah.
Okay, thank you very much. Hi, everybody. So we all know and love scaling relations. And as you know, the most important one for spiral galaxies are the Talley-Fisher relation between mass, either baryonic or stellar mass, and the rotation velocity, and the fold relation between specific angular momentum and mass. And in this particular study, we wanted to study actually the high mass hand of this relation, so above 10 to the 11 solar masses in stellar mass, because a few claims have said that this relation may be broken. So this means that maybe very massive disks have very different evolutionary paths than less massive disks. So what we did is basically collected a number of sample of massive disks. These are very rare, so difficult to get. So we got 15 H1 observed galaxies in the local universe, plus 43 H-alpha slit observation from SALT for massive disk up to redshift 0.3. We did a very of the kinematics, and we put the galaxies on the scaling relation. This is the result for the Tully-Fisher relation. In red, here you can see the H1 sample, in green the H alpha sample, while in cyan is like lower mass from the literature. And as you can see, both relation is stellar and baryonic Tully-Fisher. They are very straight, one single unbroken power law over basically 4 order of magnitude and more. Same thing is for the fold relation. Again, we could not find any statistically significant band in this relation over the entire mass range. Another interesting thing that I wanted to mention is the so-called retained fraction of specific angular momentum of these galaxies, which is the ratio between the specific angular momentum of baryons to that of dark matter halos. And as you can see, this ratio is basically constant across all ranges in mass, and it's not only constant, but it's also very close to unity, which means that doesn't matter how much messy the evolution of a galaxy is in its history, but the baryons in the disk have basically retained the same angular momentum of the dark matter halo, which is very impressive if you think about it. And I want to conclude saying that these unbroken power law are in stark contrast. Actually, we stark contrast with the stellar to halo mass relation, which, as you know, has a very big turnover, had a halo mass of about 10 to the 12 solar masses. And if this is true, we expect a similar break also in the scaling relation, which we do not see. And Mike, in a second, will tell you why actually this is not a big problem.
Can we go to the next slide, please? So the time for a lightning talk is so limited that I decided to try to put the entire contents of my talk into the title, which is given there. Are the dark matter halos of spiral galaxies as massive as those of elliptical galaxies? Do spiral and elliptical galaxies live in the same kind of dark matter halo? The answer is an emphatic no. The dark matter halos of spiral galaxies are much lighter at a given stellar mass than the ones for elliptical galaxies. And I'll show you the evidence for that on the next slide, please. Okay, so here's the evidence. There are 2 data sets. Enrico just described the one for the spiral galaxies. These are based on extended H1 rotation curves, and that's crucial. Okay, these rotation curves go out to somewhere between 5 and 10 effective radii of the stellar part of the galaxies. And then for the elliptical and lenticular galaxies, the early type galaxies, in another study with with Lorenzo Posti, we've studied the kinematics of the globular clusters, and those also extend out to somewhere between 5 and 10 effective radii of the galaxies. And since we're talking about very massive early type galaxies, we have large numbers of data we have large data sets for the globular clusters, typically hundreds or thousands of globular clusters. So we have kinematic tracers at very, very large radii, and that's crucial. You can't do this with the data just in the optical region of the galaxy. Now, you can't even measure a total mass of a galaxy if that's all you have. But if you're willing to apply the condition, a prior condition, that the dark matter halos must be like those in a cold dark matter universe, a lambda cold dark matter universe, then you can actually get a total finite mass for all of the galaxies in this particular sample. And what I'm showing here on this plot now is the stellar mass of the galaxy in the vertical axis against the dark matter halo mass. That's the mass within R200, basically the virial radius of the dark matter halo. And you see, if you project horizontally along this diagram at a fixed stellar mass, the early type galaxies, the red symbols, are far to the right of the blue symbols, the late type galaxies. So this sample for the late type galaxies is the spark sample augmented by the high mass end of the relation that Enrico just told you about. And the data for the early type galaxies come from the globular cluster kinematics. And you can see that there's about an order of magnitude at a stellar mass of 10 to the 11th solar masses the elliptical galaxies live in halos that are 10 times more massive than the spiral galaxies. And so you can, of course, divide one of these things by the other, and that's plotted on the next diagram. So that's the ratio of the stellar mass to the halo mass versus the stellar mass. So this is the so-called stellar mass-halo mass relation. And in the gray shaded region, you see the results from abundance matching. This is the study is from Moster, Baruzzi, and others, that this relation has a peak. You'll see this, you've seen this already today, and you'll see it some more later. And you see that the early type galaxies do indeed follow that, but the late type galaxies do not. They're on a monotonic relation. So late type galaxies do not follow the Moster relation. They do not follow the abundance matching relation. They do not follow the relation for early type galaxies. Next slide. So I'm concluding now, at a fixed stellar mass, I'm just repeating what I just said. At a fixed stellar mass, the dark matter halos of late type galaxies are less massive than those of early type galaxies. This is not a small effect. It's an order of magnitude effect. It's not a subtle effect. It's a easily detectable effect if you have the right data set. The stellar to halo mass ratio of late type galaxies and early type galaxies are very different. For late type galaxies, for the spiral galaxies, this is a monotonically rising function. As far as we can see, it's consistent with a power law. It rises to such a high level that there's very little missing baryons in massive dark matter, in massive spiral galaxies. They've essentially used up almost all of their baryons in making stars. They do not have much of a CGM left. And that's in contrast to all low mass galaxies. On the other hand, for early type galaxies, we get the familiar bend in the stellar mass-halo mass relation. And that's consistent with the abundance matching results. The reason it's consistent with the abundance matching results is that most of the high mass galaxies are actually early type galaxies. So when you do studies of the overall population of galaxies, you end up producing a stellar mass-halo mass relation that's dominated by spiral galaxies and elliptical galaxies at the low mass end, but it's dominated by the elliptical galaxies at the high mass end, and they do have that turnover, and that's why you see it in the general population of galaxies. Okay, thank you.
One question? Okay.
Thanks. This is really interesting and fascinating work. I'm wondering if you can comment a little bit on what is causing this differences between morphological types, in the sense that we're often told that it's, AGN quenching, for example, that causes, the down bend in the abundance matching relation. But how could that, lead to such big differences in terms of the dark matter halos?
That's exactly the question that I hope somebody would ask, because there's a fascinating answer to that one. The black hole, the AGN feedback is caused by stuff falling into a black hole, okay? And black hole masses are proportional to bulge masses in galaxies. Late type galaxies don't have big bulges, so they don't have much AGN feedback, so their stellar mass-halo mass relation isn't turned over. We should have expected this. We should have expected to find this result. It's not a puzzling, paradoxical result. By the way, it also explains why all the scaling relations for disk galaxies are power laws as well. It's because they don't have bulges, they don't have black holes, they don't have AGN feedback at the same level that ellipticals of the same mass do. That all makes sense.
Okay, thanks all the speakers, and let's come back around 1:30. Yeah. Right. Okay.
Hello, this is Surud. Is there anyone in the room? I just wanted to check that the presentation um, can be shared and my screen can be shared and my voice is audible in the room.
You can go ahead and test my, PowerPoint.
Okay, thank you.
So just give you some context.
That's what's the video. Yes, that is the video.
Can you see my screen? Hello, can you see my screen?
Hello, I'm online, and yes, I can see your screen and hear you well. I'm just not sure about people in the room.
Ah, right, yes. So that's exactly what I wanted to check because
Yeah.
I've seen in previous sessions that online people were able to hear, but there was trouble getting the audio to the room. Yeah. I suppose there's no one from the room available. Okay. I'll check later. Thanks.
and welcome back to this focus meeting on dark matter in different, different flavors and different aspects of dark matter. And so, in this second session, it's we continue with observational constraints in general on dark matter. And so, the first speaker is Kyle Oman, who will talk about dark matter cusp and cores. So the floor is yours. You have this. There is a forbidden thing here. Don't touch this. And maybe just before he starts, since I'm here, I recall that there is a Slack channel, and so we don't always have time for everyone to ask questions after the talks. So if you have more questions or if you want to engage in discussions on Slack, that's possible. And that means also that for the speakers, do have a look at Slack from time to time, because maybe there are questions for you. Thank you.
What's the slide?
So this is the slide, and this is laser.
Back.
This is back.
Right. Hi, everyone. So I changed the title a little bit from what's in the abstract booklet, but well, close enough, I guess. I thought I'd, so I assume if you're sitting in this room, you've heard of this problem before, because it's a bit of a tough nut to crack, right? It's been plaguing us for close to 30 years now. I've given this a lot of thought, so I thought I'd give a sort of quick review and then my own perspectives on how might we finally settle this question. Okay, so let's go way back. So if you think of the simulation prediction that dark matter halos have central cusps, so the density rises steeply towards the center. Maybe you think of Navarro, Frank, and White 96, but it actually goes even a little bit further back than that. Pretty sure the earliest reference is from 1991 from this Dubinsky and Karlberg paper, right? And there you see the dark matter density as a function of radius, fit with a Hernquist profile, and rising all the way to, well, as far in as it can be resolved at the time. And then, so observationally, there's a few different ways to do this. So I apologize in this talk. I had some slides on dwarf spheroidals and stellar kinematics and things, and I eventually took them out just to make it all fit. So I'm going to focus mostly on the sort of a H1 gas rotation curve probe of this, right? And there, so people talk about measuring rotation curves, and there's a sort of important distinction between a rotation curve and a circular velocity curve. So here what I'm showing on the left is two dark matter density profiles, one with the central cusp in blue and one with the central core that flattens out in red. And then on the right, that's the equivalent circular velocity profiles. And by circular velocity, I mean turning the density profile into an enclosed mass profile, and then the velocity that a particle would have on a circular orbit in a spherically symmetric potential with that mass profile, right? Which is not necessarily the same thing as the actual orbital speed of a tracer particle. Okay. And I guess the thing to keep in mind is that the core has this telltale linear rise in the circular velocity curve near the center. And I've marked with an arrow the size of the core in the two plots. Okay. So then again, going way back to the classic references right here, the two papers that started this whole cusps versus core debate. So Flores and Premack, the two panels on the left, and then Ben Moore the same year, the four galaxies on the right. Right, and here you see, so the Hernquist profile that was fit to the profile in the very first figure I showed is again sketched in on a few of these and doesn't follow these are rotation curves measured, but interpreted as circular velocity curves for these galaxies, right? And so that's kind of a quick recap of where this all came from. And there are four solutions to why these observed galaxies might not have the cusps predicted in the simulations, right? You can redistribute the dark matter via dark matter physics. Right? So you can imagine giving the dark matter some scattering interaction so that that basically, as the density builds up near the center, eventually as you start trying to add additional dark matter density, it's going to scatter off other dark matter, and you basically put a density maximum near the center, which will form this central core. And this was already discussed as an idea in Ben Moore's 94 paper. Right? You could also kick around the dark matter through baryon physics. So I'm thinking of something like you have gas that condenses and cools in a galaxy, which is going to make the whole thing contract. And then if you explode some supernovae and expel that gas, then that's like a non-adiabatic change in the potential, which is going to perturb the dark matter and drive it out. And then you can repeat this process in a cycle and eventually carve out a central dark matter core, right? And this idea was also floating around in the mid-90s. Or it could be that we don't understand something about the law of gravity, so it's not quite Newtonian or general relativity, but something else. And even before all this discussion started, more than 10 years earlier, so there's the famous example of the Mond theory, which predicted the rotation curves of galaxies back in '83. And finally, it could be that the rotation curves that we measure are not necessarily tracing the circular velocity curves or the gravitational potential of the galaxies. And this was also thrown around as an idea. And as far as I know, this is all the possible ways out of the problem, right? And we've known all this since, well, the 80s or 90s. So why are we still stuck? Okay, so if we fast forward to 2024, there's this review led by Laura Salas. And they had an interesting perspective on this, which is to say that sort of the classical cusp core problem, in their view, is basically solved because you have a way to make dark matter cores through this supernova feedback driven gas flows, right? And that to them said, okay, well, we have a physical mechanism that is clearly very plausible for galaxies, and therefore that would seem to alleviate a lot of the tension. And so then a lot of attention in the past few years has shifted from, okay, not just can we explain how a core might exist in a galaxy, but can we explain sort of the apparent distribution of dark matter densities in the centers of galaxies, which led this paper in 2015, where we showed that at fixed total mass, you can have galaxies with very high central dark matter densities or very low central dark matter densities, and otherwise broadly similar properties. And so how would you do that? You'd have to have some connection to the galaxy formation history of these objects, maybe. But I don't think anyone has yet presented an explanation for that sort of diversity in the population that wraps up the whole story at once, right? You can explain this aspect or that aspect, but I think we've yet to arrive at a synthesis that just settles the question. Okay, so this idea of the kind of diversity in the population can be summarized in a few different ways, but here's two figures from a paper led by Isabel Santos back in 2020. And the left panel, so we've got the maximum of the rotation curve, in this case on the x-axis, which is loosely a proxy for the total dynamical mass of the system. And then on the y-axis, we've got the rotation velocity at some radius relatively close to the center, and how big that radius is just scales with the mass of the galaxy. And so that's a proxy for sort of the central dynamical mass, or in other words, how fast this rotation curve rises and whether you have a very dense center or not. And so in that space, whether you have a cusp or a core kind of scales along this diagonal. And between those two vertical lines, that's an area where we focused a lot of attention, right? You get a very big scatter along that diagonal. And so galaxies, which are otherwise broadly similar, can seem to have anything from a very, very steep, even more than like a Hernquist or Navarro-Frank-White cusp, even steeper than that, all the way to a completely flat core that extends very, very far. Right, and the right figure, so on this takes the two axes of the left figure and compresses them onto the y-axis, right? Takes the ratio of the two things, and so therefore the kind of cusp to core gradient runs vertically now. And then on the other axis, we put the square of the ratio of the rotation speed near the center and the rotation speed you would predict from how much baryonic mass is in the center. And so you can think of this as like the central baryon fraction with respect to the total mass density in the center, right? And so, low density galaxies on the left and high density on the right. By density, I mean near the center. And then these are colored by dynamical mass, basically. And what you see here is, there's some interesting correlations that pop out. How centrally dense in dark matter a galaxy is seems to correlate somehow with its central baryon density, and so that's probably some kind of hint that seems important. But it turns out that the direction that this runs from, galaxies that apparently have a cusp are the ones with low central baryon fractions, And then there's kind of a gradient. If you look at the lower mass galaxies, the darker orange point that runs down and to the right, that turns out to be a bit tricky to explain. So I like this plot a lot just because it's a good test. If you have a theory that makes some predictions, make this plot. If it doesn't reproduce this, I'm unconvinced, because it's a fairly hard test. Okay, so then where do we stand, right? I gave you the 4 possible solutions. And to me, here's where I think we are. Not so sure about the first 3. The one that I'm convinced has a role to play is the last one, right? There's something funny going on in our modeling or interpretation of the measurements. I'll give you 3 reasons for that. These are kind of the 3 most egregious examples I could pull up and show in 3 slides. So let's go through these. Right. So exhibit A. Right. So here's a galaxy that I love to pick on. This is IC 2574, highlighted by the arrow there. Right. And so let's give ourselves a prior. We're going to suppose that galaxies start with a central dark matter cusp. And then on this, very similar to the diagram I showed a couple of slides ago, we end up with a galaxy way down here. Okay, so if it started with a cusp, how did it get down here? Well, we had to remove some mass from the center. And how much mass did we remove? Well, the broken lines are labeled with masses, right? 10 to the 8, 5 times 10 to the 8, 10 to the 9. That's, if you remove that much mass from a galaxy that started with a cusp and therefore would have started on, there's a solid black line buried behind all the points there. So if you start with a cusp and remove the amount of mass corresponding to one of the lines, then you land on that line. And where the lines become vertical is basically where you've removed all of the mass from the center, right? And so the most extreme examples of galaxies we have on this diagram looks like you basically have nothing left in the middle, which seems a bit extreme, right? And there's not every galaxy is on this plot, but we have a handful of examples that lie kind of way down here where, put another way, the dark matter core you infer in these things is so large and so low density that it seems very difficult to reproduce in any kind of physical model, right? And so then kind of begs the question, is it rather something about how we've done the dynamical modeling of these systems to get the rotation curves, for example? All right, second example, these are these much discussed ultra diffuse galaxies, now placed on the baryonic Tully-Fisher relations. These are strong outliers from the BTFR. And so as a quick reminder, this is the relation that relates the total baryonic mass, so stellar plus gas mass, in this case cold gas on the y-axis, to the circular velocity. So again, a proxy for the total dynamical mass. Right? And so most galaxies lie along a very tight sequence, illustrated by the sort of blue and green points here. And then these ultra diffuse galaxies, so these are very low optical surface brightnesses, lie way off to the left. Okay, and so this is work led by Pavel Mancera-Pina. And we were both in Groningen at the time, and I remember him coming to my office and saying, look at these. And I looked at this diagram and said, yeah, okay, you got the inclinations wrong. And after some weeks, he convinced me that this was not the case, and we went through many other possible systematics in the modeling, and also, physical interpretations. Could these just be the extreme low concentration end of the dark matter halo distribution? Could these be high spin halos? Could these be just have peculiar star formation histories? Nothing really sticks. And so to me, either you have to assume that these things have a baryon fraction equal to or higher than the cosmic mean, which feels very uncomfortable. Go to some kind of new cosmology, which also feels fairly uncomfortable. Or there's something funny going on with the modeling of the data, which applying Occam's razor seems like my preferred way out of this, although, final word is yet to be seen. And finally, kind of on a related theme, here's another galaxy where, if you looked at this, you'd say this has way too many stars and gas. There's way less dark matter than I'd expect for the amount of stars and gas. But this particular example has the benefit of also having stellar kinematic measurements, right? So the measured rotation curve is in the black points. What you might expect from something like an abundance matching prediction from a simulation is kind of the red band, right? So we're not rotating fast enough for our stellar mass or for our gas mass. And then this blue point is a kind of one aperture dynamical mass measurement coming from stellar kinematics, which doesn't agree with the gas. And so the fact that those two measurements don't agree tells you that one of them's wrong, because they're both supposed to trace the dynamical mass within that aperture. And one way out of this is you say, well, let me assume that I got the inclination of the gas disk wrong and just correct that until it agrees with the stellar kinematics. And then all of a sudden, everything looks fairly sensible, although this galaxy does still look like it has a very large dark matter core. Right, so there are just three examples to say that it looks like there are fairly serious systematics, at least in some galaxies, which suggests that there could be more subtle systematics in the modeling of other galaxies. Okay, so then we want to try and untangle this, and to me, until you understand the galaxies we're looking at and what the data are telling us, it becomes very hard to come up with a theoretical model to explain what's going on. Right? It's kind of like you don't know where the target is. So what do we aim for with theory? Right? You could come up with a beautiful self-interacting dark matter model that explains the measurements perfectly, and then you realize that all the measurements were, had the scatter inflated by a factor of 2, and suddenly your model doesn't look so good, right? So it'd really be nice to know what we're aiming for with theory first. Okay, and I find it helpful to break this kind of problem into two aspects, right? So there's two parts. Are we accurately recovering the dynamics of the gas or of the stars or whatever tracer we're looking at from the measurements, right? So you always have observationally some limited information, which you then have to interpret to get like an enclosed mass, for example. And then the somewhat more pernicious question of, do the dynamics of whatever we're looking at actually trace the underlying potential, or are we looking at, for example, a galaxy that's strongly out of equilibrium, where that's going to become very difficult to interpret the dynamics of that system as a tracer of the underlying gravitational potential. Comment briefly on both of these. So I think the question of, do the dynamics trace the potential? Right now, I think the way to attack this question is mostly from the theory and simulation side. I feel like that's where we're going to make the most progress right now. And so these are two recent bits of work. One that I was involved in, where we looked at a number of simulated dwarf galaxies and just asked, in what ways can these galaxies be perturbed, and how often does that happen? And the answer is in many different ways, and very, very frequently. And I pulled out just my favorite figure from this work. So on the y-axis here, this B over A, this is the axis ratio of the dark matter halo. And so if it's intermediate to major axis. And so if this is 1, then you have either a spherical or oblate halo. And as it becomes less than one, that tells you have a prolate or triaxial halo. And as soon as the halo is even slightly triaxial, I should explain the other axis, sorry. This Q is some measure of how well the rotation curve of the galaxy traces its circular velocity curve, right? You can go to the paper if you want the details, but basically Q equals 0, good. Q greater than 0, bad. Right? And as soon as the halo becomes even slightly prolate, you get a huge amount of scatter. And this is basically because an oblate gas disk does not want to sit in a prolate halo in a stable way, and so the disk is constantly knocked around just by the fact that it's sitting in a slightly prolate dark matter halo. And most halos are slightly prolate to some extent. You can see an axis ratio off by 5% is enough in many cases, right? And then the other piece of work I'll highlight was led by Isabel Sands in Phil Hopkins' group in the US. Couldn't find a nice figure that I liked from that paper, so I pulled out this table instead. And what they did was look at simulated galaxies in great detail and look at the stress energy tensor. So all of the different contributions to the rotational support of the disks, including just the fact that it's rotating, pressure support, magnetic pressure, everything that they could decompose it into, and looked at all the different combinations of these terms to really pick apart, in what ways can a galaxy be perturbed, and can the rotation speed depart from what you would expect from just pure gravitationally driven rotation in the gravitational potential. Okay, and then the other question, so are the dynamics correctly recovered? So I think the main point I want to make is that modeling observations to get this is difficult. You have limited information, and that's fine. And I think the thing that we're really missing in this area is better estimates of the uncertainties, right? You can tell very clearly looking at rotation curve measurements that in many cases, the uncertainties on those measurements are underestimated, even just from like the point-to-point scatter in the rotation curves. And that really makes it difficult to interpret them. So, like there's been some motion in this direction, quite like a paper by Jerry Selwood and Christine Speckens lately on the better uncertainty estimates on rotation curves. And my chair is standing up and I'm on my last slide, so that's good. And so, yeah, I think we need some work from the theory side. We need some work on the modeling side. More data never hurts, although that's kind of a cheap way out. We're going to get lots more data, so that's good. And I've kind of glossed over a little bit because I suspect Federico is going to talk about this later in his talk about connections to other scaling relations, especially the radial acceleration relation that also play an important role in this whole conversation. So thanks very much.
Okay, so there are quite a number of questions. I'll start.
Hi, Kyle. Thank you so much for the talk. So, okay, about your last point, the fact that our model for modeling the rotation curves probably are not super appropriate for dwarf galaxies. So, what do you think is the problem there is like the fact that we often assume like a disk model, we need like to take into account more, circular motion or, the thickness of the disk. Why does it fail so badly? I think it's not just the uncertainties, it's also the rotation curve that we get. They're not great.
So most models for these galaxies are based on the tilted ring idea, right? So you chop your disk into concentric rings and then fit the rings and probably do some sort of, well, exactly how this works. Of course, you've written the code. And to me, it feels like I have to go back to the drawing board a little bit, right? One of the big limitations in these codes is you tend to fit ring by ring and then do some kind of regularization and fit again. When you get to dwarfs, they're geometrically thick, the rings overlap. Probably you should be optimizing the entire problem in one go rather than bit by bit. So I wonder if...
So there are codes that do that. Actually, have you ever tried like Terrific or FAT?
Yes. But I still feel like all those models kind of started from let's model warped giant spirals and maybe going back to the drawing board and being like, okay, what's the best way to actually model a dwarf irregular is not a crazy idea.
Yeah, thanks, Kyle. Really nice talk. I wanted to ask you, because I know you share this view that simulations don't tell us reality, but they tell us what may happen. And specifically for the last plot, not the last plot, but when you were showing the different rotation curve that you get from the simulations, I wanted to ask you, in your opinion, how much do you think is really a problem when it comes to real data, in the sense that I saw that many of them, for example, show spikes or they are very irregular. And with real data as observers, if you get something like this, you probably wouldn't even fit, ideally, a mass model or something like that. So I think in many plots we have seen around, you don't have galaxies as messy as those.
Yeah, so I feel very lucky to have worked so much with simulations that are so messy and unrealistic, because they exaggerate all the effects and makes the kinds of things you might worry about in real data easier to see and more obvious. And so my take is, yes, I agree. The simulations are messier than real galaxies. They have these wiggles, spikes, bumps, whatever. And probably you would shy away from these observationally. But studying those simulations, I think I've learned a lot about the kinds of issues we run into. And I mean, my take is it seems very reasonable to me that the same issues affect real galaxies to a lesser extent, right? The amplitude of the scatter is probably less observationally. And so if you want my one-line takeaway from the talk, right, is it systematics, we figure that out and then everything has a cusp? Probably not. It's more like we're left with some distribution between some galaxies that look like they have cusps and some that have cores, but it's probably not as big as what we think we see now.
Beautiful talk, thank you. I have a question about one of the final plots that you show, the rotation curve, the observed one, and the true ones. In that figure, to me, it seems that past 6 kiloparsec, the deviation between the observed rotation curve and true rotation curves become more prominent. Why is that? Because I expect the opposite, like closer to the center, I expect the difference between the observed rotation curve and the true one become more significant.
This was in the simulations, right?
Yes.
Okay, I can give you the long answer later. The short answer is that as you get out to those large radii, you start running into the transition between a atomic gas-dominated disk and an ionized gas-dominated halo. And these particular simulations, there are challenging issues around that. And so I wouldn't pay too much attention to that. I think we understand where that's coming from, and just it's not.
So it's a matter of simulation, not physics.
Yeah, it's just a limitation of those particular models.
Thank you.
We'll take one last question. And maybe the next.
Hi, Kyle. So my interpretation of your simulation results is very different. I think that the simulations are totally unrealistic in that regime because they probably have too much non-circular motions that drives things out of equilibrium. Otherwise, we wouldn't be able to observe the tight empirical relationships that we do observe, like the baryonic Talley-Fisher. If everything was out of equilibrium, we should see scatter plots, but we see tight relationships. So my question is, what if one does a step back, simulates an isolated low mass galaxy with a weak stellar feedback? Would that be in equilibrium?
So, yeah, our study of the different ways that a galaxy can be out of equilibrium, we identified a number of things. Right? There's supernova-driven gas flows, which if you turn down the feedback, that'll get better. But this question of like, if you have a prolate dark matter halo, for example, there's no stable configuration for a gas disk in a prolate halo. And so if you give your low mass isolated, gentle feedback dwarf galaxy a prolate halo, it will still have strong non-circular motions and be out of equilibrium, for example. And there's more, we can talk more later about other options.
Yes, we'll shift to the next person presenting. Thank you. And so that will be Catherine Czerny on probing the inner density profiles of dark matter halos.
Hi, everybody. I am very happy to be here. I wrote this abstract a few months ago with somewhat of a different plan in mind, but I literally just successfully defended my PhD 3 weeks ago. So I'm just going to talk to you a little bit about what happened in my thesis. Thank you. So to sort of, sorry. How does this work? Sorry. Okay. Thank you. Okay, great. So I'm going to follow up a little bit with what Kyle actually talked about with cusps and cores, but I am showing you a picture of a galaxy cluster. So I am not talking about galaxies, and I hope this is okay for everybody, but I'm talking about this problem in galaxy clusters. So this is Able 383. I'm bringing it up because it has this nice little feature here, and just so I can explain this very briefly, this is an example of strong gravitational lensing. This is something that happens when light from a background galaxy travels through the potential of a cluster, and that light ends up creating multiple images around the cluster of the same background galaxy. We can use those as constraints then on the actual mass potential of the cluster. But this cluster is particularly special because of its BCG and what's sitting next to its BCG, because there's actually a multiple image there. This doesn't show up super great in this image, which is another like HST version of this, but over here there's a GalFit extraction, and you can see there is definitely an arc there. This is a wisp of emission, so this is the same background galaxy as this one actually. So why am I showing you a cluster? Why am I showing you radial arcs? because I am also looking at the cross-core problem from the perspective of galaxy clusters. This was already explained pretty well by Kyle last talk, so I will just say that this problem exists all the way from dwarf galaxies to scales up to clusters. This is something that it's kind of universal right now, and it's not super well understood on the cluster side yet. Especially because cluster-specific simulations recently that have included like baryonic feedback and such find some slope values that are quite higher than 1. So anything less than 1 is going to be a core, and anything greater than 1 is going to be more of a cusp. So I made this very quickly, kind of just as a general look at cusp core at a few different scales, but you can see that the observations kind of tend to be lower, although there is some agreement at this cusp-like shape, and simulations on the whole tend to be higher. So from an observational perspective, this implies that we need to do a bit of detailed modeling to understand what is going on with the cusp core problem, right? We need to address model systematics, and we need to also check and see whether alternative methods of or alternative models of dark matter could potentially explain this difference. And on the cluster scale, something we're interested in is looking at self-interacting dark matter pretty particularly. So this is a figure from, I keep pressing the wrong button, sorry. This is a figure from Robertson 2019. He's basically doing some simulations of clusters, and the SIDM models that he uses have these colored profiles, and then the CDM model is the black profile. So to distinguish between these observationally, we kind of need a percentage. We need to have a precision on the uncertainty percentage of about 5%. Without that, we can't really say too much about whether or not SIDM is a viable alternative model. So achieving that precision on the observational side can be done with maybe around 20 clusters. This is assuming Gaussian uncertainties and just sort of standard statistical combinations. So to get N20 in order to understand whether or not SIDM can potentially be an alternative model, we need lots of different models, right? We need lots of different clusters, and we need to do lots of models. Obviously, doing a full dynamical mass modeling treatment of all of these clusters would be best, but this requires telescope time. This requires investment in modeling. This requires a lot of hours. And also, this is a little bit challenging to do at scale, right? And especially as we're getting more different surveys and more different, like large scale surveys rather, it's kind of interesting to see what is the minimal, like the cheapest sort of model that we can build to actually understand this problem. So this is something that I sort of looked at in my thesis in clusters specifically. So within the inner 50 kiloparsecs of galaxy clusters, you basically have two majority dominant components, and these are the baryons that are contained in the BCG, the brightest cluster galaxy, which are these big ellipticals that are sitting at the center of the cluster potential-ish, and then the dark matter of the cluster halo itself. So if we create a mass model that's only including these BCG baryons and the dark matter of the cluster halo, can we get close to actually understanding what this inner slope measurement would look like inside of these clusters? And so the way I'm doing this is by taking the BCG mass and measuring that using stellar kinematics, just dynamical mass modeling. And then for the dark matter mass, I'm using strong gravitational lensing. To make this as robust as possible, I'm also using clusters with radial arcs. So remember, Bagel 383, these radial arcs are multiple images that are located super close to the BCG. So I'm talking within like 10 to 15 kiloparsecs. Now, the location of those radial arcs means that for strong lensing, we have a constraint that is incredibly close to the center of the cluster, which means that we can use strong lensing mass model to really understand what's happening in this inner portion of the cluster, which isn't something you can necessarily do without clusters with radial arcs. I'm looking at a total of 8 clusters. I've shown 6 of them here because this was this was the room that was available to me on the slide. Radial arcs are a bit hard to see in HST data sometimes, so I've also shown you these Muse contours, which show you where they are. So the white lines are the Muse contours, and you can see here, this is a counterpart to this radial arc here, and this is a tangential to this here. So you can kind of tell these are associated together because they're showing up at the same wavelengths in Muse. All of these clusters are pretty relaxed, and all of them have nearly circular BCGs, which means we can kind of get away with making some simplistic assumptions about mass modeling as we go through this. And they're also good to compare with simulations that have these equilibrium DM halos. We're trying to be as simple as possible. A few of these have been modeled before, but the improvements I'm bringing to them are after 10 years later, we have VLT Muse available to us. We have IAU data available to us. So that's what I'm kind of adding on to a couple of these clusters. So I'll just start with the strong lens modeling because I am like a cluster person. So this is Able 383 again. You see the Muse field of view here in orange. You can see this is capturing basically the entire strong lensing regime, which is super good. The red line is showing you the critical curve of the strong lens model. This is basically where the magnification is equal to infinity. And it's also showing you where most of the mass of the cluster is sitting in this strong lensing region. And then the white numbers correspond to the multiple images. So there are 9, I think, systems of multiple images here, and then 9.1, 9.2, 9.3 are all the same system 9 with 3 different images. I'm using Lens Tool to create these mass models. So this is, again, kind of trying to get into a parametric breakdown of the different mass components of the cluster. Lens Tool is MCMC modeling as well. I break up the mass components of the cluster into basically 4 different components. So I have a cluster scale dark matter halo. I have galaxy scale dark matter halos around perturbers, and these would be like this guy over here, which is right next to a bunch of multiple images. So it's having some effect on the mass potential that's driving that creation of the multiple images. I have cluster member galaxies scaled using the Faber-Jackson radiation, and I have the BCJ. One thing I will note before I go further is that for this cluster scale dark matter halo, something that I've done that's kind of new is I've not used an NFW profile. I haven't really gone into detail here in this talk about why and all of this because I figured it wasn't super relevant to the session. But essentially, NFW modeling is very, very susceptible to bias inside of lensing specifically. And so if you do not have a very well-defined constraint on your scale radius, essentially, you can get inner slope measurements that vary really, really wildly. So in order to avoid that, I've used instead a dual pseudo isothermal elliptical mass distribution profile, which is something that is very favored in the cluster lensing community in general. And I can talk more about that later. For the BCG, I've also wrapped this into this parametric model, but I'm constraining the BCG baryonic mass using Jeans dynamical modeling. So the familiar equation is here. We have the velocity dispersion, we have the 3D stellar mass, we have the 2D stellar mass, and then we have the total enclosed mass at some radius. Cool. In terms of the stellar kinematics, I'm running out of time, so I'll gloss over this very quickly. But essentially, one of the things that drove this project was that I am using Muse data from the Kaleidoscope survey, which is a non-priority filler survey hosted up at Durham, and it consists of about 250 different clusters. So one of the things we wanted to do was really exploit this data set to its maximum potential. This data set is a bit noisy and a bit shallow, so I experimented with making different apertures to measure the velocity dispersion profile, which is again coming into this Jeans modeling. I'll skip this, but essentially, if you make a circular annulus on your Muse IFU cube and you take that out over the radii you're interested in out to a certain point, you can get results that are comparable with these deep exposures from something like Keck-Galerius. This is a nice result. I'll skip this other than to say that I'm using a saltpeter IMF to get my BCG profiles. So this is maybe a controversial choice if you're a galaxy person. Maybe we can talk about that. So here are the results. For these clusters that I'm looking at, I get kind of a spread of values. As you can see over here, I want to emphasize that these two clusters are made with like one HST filter and 2 HST filters respectively, but they have Muse IFU data that provides different strong lensing constraints and provides these Muse velocity dispersion measurements, which allows us to make simple models that give us this inner slope measurement. And then to place these simple model results in context with literature, I have a selection of just different observational papers of clusters here on the bottom. against the inner slope. And then this blue line here is coming from simulations out of Sea Eagle at about like 1.0. And my results are very in context with literature, but I also want to emphasize that there is still a very distinct spread in these slope measurements from observational papers. So this is something to keep in mind, that we really kind of need to do a bit more work to understand this problem. And then I will just end with my summary because I am out of time. So thank you.
Okay, questions?
It's a great talk. Just one question about the slopes. When you said it's at 30 kilo or within 30 kilo per second, what is exactly the slope that you're measuring? Is it like just like average slope within 30 or like near 30? What is this slope?
Yes. So that is dependent on the cluster itself, but essentially I'm taking it from the inner like 0 to around 35 per cluster, the dark matter halo only. And this is something that we're able to do because we are doing this parametric mass modeling, which breaks up all of the different components into dark matter and then all of the baryonic stuff. So we can subtract the baryonic components out of the total mass profile, get the dark matter, and then measure that slope.
Nice talk. I may have missed this piece of information. What are you doing regarding the orbital anisotropy?
Yes. So anisotropy is not something I had time to get into here, but I'm basically using GemPy and then varying it to a constant value of around 0.2. And these don't really affect the results so much. BCGs don't have a lot of anisotropy generally, but I think the difference in between these constant numbers is like 5%. So this is something that isn't really worth talking about in the talk, but this is something I have in my paper.
So you are assuming that it's radially constant?
I am assuming constant anisotropy, yeah, because these are pretty circular BCGs and not a lot of activity happening in the cluster.
So there is still time for one question, maybe?
So if I understand, you said that you are not using an NFW profile for the dark matter, but what is the profile you are using? It must be something that allows you to have a different slope in the center distribution.
Yeah, actually, if you can put my slides up, I have like an extra one at the end. So I'm using a dual pseudo isothermal elliptical mass distribution profile. This is abbreviated as DPIE or PIMD, depending on who you ask. This essentially breaks up the mass profile of the cluster into an inner part, so a core-ish part, and then an outer part. So not a cusp, like R2 to like R4, etc. But the nice thing about this is that the core profile part is very flexible. And so a DPIE profile is actually capable of reproducing these cusp-like slopes. And this is something that I can see in the cluster Max 1423, where I can get the exact same value as an NFW profile without the assumption of the scale radius, which is, again, a very, very biased component of lensing models in general.
So I think we'll end here, so we can thank the speaker again. If you have more questions, don't hesitate to ask on Slack. And so the next talk will be a recording, in fact, but because the speaker who is Carlos Melo Carnero is sick, but he will be able to answer questions afterwards. So,
interested in early type galaxies, which you may know are gravitationally bound systems formed of stars, planets, and something we call dark matter. The systems, they are typically red and very old, and we understand them as the end product of the galaxy formation and evolution. And the interesting thing about the systems is the fact that they share a lot of scaling relations, and many of these scaling relations are related to the mass distribution of the galaxies. And just as one example, in this plot here, I'm showing the time evolution of the total mass logarithmic slope for ETGs in the TNG simulation. And based on results like this one, and also based on results coming from observations, we were able to build the two-phase evolutionary scenario, which is a way to interpret how galaxies evolve with time. But related to the mass distribution of galaxies, we have many other properties that we can derive and study, such as the assembly history, the stellar content that we can use to calibrate IMF. We can also have some probes on dark matter distribution and also probes on alternative theories of gravity. But to measure the mass distribution of galaxies, we have a few approaches, such as dynamical modeling, gravitational lensing, and SID fitting. But today, I want to talk about how to self-consistently combine strong gravitational lensing and stellar dynamics. Because in principle, once combined, these two approaches can break intrinsic degeneracies that are present in the individual models. And by doing this combination, we can also have more reliable and robust measurements of the mass distribution. So as I said, the goal of this talk and also of this work is to show how to combine different tracers of mass profile to reduce intrinsic degeneracies. And I also want to provide some insights into the biases present in such self-consistent modeling. In particular, we'll be highlighting some results regarding the biases in the total mass, stellar mass, and dark matter quantities. So to do this combined approach, we'll be using the multi-Gaussian expansion formalism, which is a way to parameterize the surface brightness profile and convert this to the project stellar mass distribution. But we can also use this same formalism to parameterize a dark matter profile and include this contribution into our mass model. And using this formalism, we can also simultaneously solve the lens equation and the Jeans equations. So using this formalism and three other codes called Pareto Lens, Dynasty, and Gem, we built a new framework called DyLens, which allows us to perform self-consistent modeling. But we can also use DyLens to perform just dynamical-only modeling and just lens-only modeling. And all these three modelings using the MGE parameterization for the mass profile. So to test this framework and also investigate the biases, we create a sample of 21 mock observations using elucidity energy hydrodynamical simulation. And these mocks, they have AST and Muse-like features, such as the same pixel resolution and a similar signal to noise. And the idea is to model these mock observations using the combined approach, but also the lens-only and the dynamical-only models, and then combine three different methods and see the improvements and how the results change. So to model this sample, we'll be applying this mass profile, which consists of a constant stellar mass-to-light ratio, a constant stellar anisotropy, and a GNFW profile. And this setup is very similar to the one used to create our mock sample. So talking about the results, here I'm showing the fractional difference or the bias in 3D intrinsic enclosed quantities within 2.5 effective radii. In black, I'm showing results coming from dynamical-only modeling, and in blue, results coming from the combined modeling. And the upper left panel, I'm showing the bias or the fractional difference in the stellar mass, then the bias in the dark matter mass, the bias in the dark matter fraction, and the bias in the total mass. And the numbers here are the median of the distribution with the 1 sigma spread. So as you can see, for the median values, but also from the distributions, both models are really good in recovering the stellar mass and the total mass with a bias below 10% in both cases. and a relatively low spread in the total mass. But unfortunately, the models struggle in recovering the dark matter quantities, such as the total mass and the dark matter fraction, with a bias reaching to 32% for the dynamical modeling when trying to recover the dark matter mass. But also there's an issue with the spreads. I mean, the spreads are quite large around the median, which is not very good as well. About the results regarding 2D enclosed quantities within the Einstein radii, again, I'm showing the biases in the stellar mass, dark matter fraction, and total mass. And now in red, I'm showing results for the lens-only modeling, and in blue, again, are the results for the combined modeling. And as we saw before, both models are doing a decent job in recovering the stellar mass and the total mass. But again, the dark matter mass is not well constrained. We can see the spreads are quite large, and the bias are also quite large. But an interesting thing here is the fact that both models recover the dark matter fraction within the Einstein radii with a low median bias, around 10%. But the downside with this is the fact that the spread around the median is very large, covering almost the whole interval, which is an issue if you are interested in model just a couple of galaxies. On the other hand, if you are interested in model a very large sample of galaxies, which will be available through the recent large area surveys, then this result is interesting because this means that we can have a relatively low bias on the median trend. And finally, one last result that I want to show you is how the number of kinematical tracers impact the outcomes. So what we did was create a new data set for the kinematical data, varying the number of beams on this data set. So in black, I'm showing results for the data set where we have 35 beams. In blue is the data set where we have 50 beams. And then in red is the results where the data set have 55 beams. And all these results are for the combined modeling. And as you can see, varying the number of kinematical tracers doesn't seem to impact the outcomes, which is really interesting because when you are thinking about observations of intermediate and right redshift galaxies, the number of beams will be very low because a few observations requires lots of interrogation time, and the number of kinematical beams will be just a few because we don't have like all this time to reach a very high signal to noise, and we will need to bin the data. So before my take-home messages, I just want to say that I have more results regarding the total density slope and also variations on the dark matter assumption. So if you want to know more about this, just come talk to me. I'll be very happy to chat about this. But the take-home messages is that all models, they are really good in recovering the total mass. All models are also very bad in recovering the dark matter quantities, which is an issue. But the models seems to be insensible to the number of kinematical constraints, which is an interesting result. You can also check the details and more results looking at the paper that is now on arXiv. So you can just scan the QR code here and check the paper. And yeah, I think that that's all. So thank you very much for your attention, and I will be happy to take some questions.
Other questions for Carlos? I hope he will be able to answer on Zoom. So maybe I have a question, which is that in your joint modeling, you are trying to model two things that are quite different in terms of observables. So do you need to assume some kind of weight between the two elements that you put in your modeling, and to what extent does the result depend on that?
So I hope that you can hear me.
We can hear you. Yes, perfect.
Yeah, so very nice. So thank you for the question, and also thank you for the opportunity of present this online. But yeah, we have very different data sets. But in this case, we are not putting any weight on the different data sets because it's not very clear how we should do this thing, if we should do this thing. Because we are doing some MC analysis, so Bayesian inference, and it's not very clear how to weight different data sets. Because, yeah, as I said, it's not so easy to do this thing without introduce some unknown bias in the modeling. So what we are doing is just combining the likelihoods because the data sets, they are independent. So we can just multiply or sum the logarithm of the likelihoods, and we are doing the full modeling in this way.
Okay. Other questions?
Very nice work. Regarding the uncertainties on the dark matter fraction, is this a consequence of the dark matter being such a small fraction within the aperture that you're considering?
Yeah, this is actually a good question as well. And I think that this is not the main issue with the scatter and the bad recovery, because we have different values for the fraction of dark matter within our aperture. And we believe that the major problem with this bad recovering comes from the fact that our data set is not covering the dark halo well in terms of extended, because our data set has data around 2.5 effective radii, which is not a very large area. And the scale radii of the halo, it's much more extended. So when you look at how well we are constraining the dark matter scale radii, we saw that we are not constraining this parameter in any way. So this is impacting our outcomes because all these parameters are very degenerated in the modeling. So I think that this is the main issue that is really hard to solve without having more constraints in a large area, in a large radii.
Okay, so I suggest we thank the speaker again. And our next speaker will be Jessica Doppel, and talking about imposters amongst us.
That's good. All right. Make sure this is working. Yes, good. All right. Hi, everyone. I'm Jessica Doppel. I am a postdoc at Durham University. Okay. And I'm very happy to tell you all about what we can learn about what globular clusters can tell us about the dark matter content of ultra-diffuse galaxies, specifically those in galaxy clusters. So first, a little bit of background about why we care at all. So globular clusters are pretty much ubiquitous in the universe. Pretty much every galaxy above a stellar mass of about 10 to the 9 solar masses hosts at least one globular cluster. These objects are super old, with stellar masses between 10 to the 4 and 10 to the 6 solar masses.
crammed into just a few parsecs. This makes them quite bright and easy to be observed over large distances. Now, more interestingly about globular clusters, at least in my personal opinion, is that they may provide us a relatively cheap way to trace the dark matter content of their host galaxies. So this is the famous globular cluster mass, halo mass, that we've seen at several points today. And we can see that there is a very tight relation between a galaxy's total globular cluster mass and its halo mass. And there is a little bit of an open question about whether or not this does extend into the dwarf regime, as others have mentioned. And this is something that we have sought to test in simulations, and a little bit more about that later, though. So ultra diffuse galaxies, why should we care about them? I mean, for obvious reasons, they're cool. But these objects are extremely radially extended for their stellar masses. As others have shown, these are things that have roughly dwarf stellar masses with radii more on par with galaxies like the Milky Way, which gives them very low surface brightness. But they tend to be quite diverse in their globular cluster content. So this is showing, go back. Aha. So this is showing specific frequency, which is a measure of globular cluster abundance as a function of their host galaxy's V-band absolute magnitude. And we can see that for UDGs, which are in these Siam points, we get a very wide range in our globular cluster abundances, more so than the normal dwarfs that you would expect in this particular cluster. Now we additionally see this diversity in UDG properties in the velocity dispersions of their globular cluster systems. So this is showing velocity dispersion versus V-band absolute magnitude. And we can see that in particular, again, drawing your attention to these Siam points, that there is a very wide range of globular cluster velocity dispersions that we find. These are UDGs in the Virgo cluster, ranging from things that appear to be relatively dark matter deficient to things that are on par with the velocity dispersions of early type galaxies, so more elliptical systems in these clusters. So this could be an indication of a number of things, including a diversity of host halos, or perhaps a diversity of formation mechanisms. But in order to really probe how these things are tracing dark matter, we need to turn to simulations to understand a little bit the systematics. So globular clusters have been sort of a notorious issue in simulations. They are sort of the subject of a multi-scale problem. So we have sought to overcome this by implementing a post-processing globular cluster tagging model in the TNG50 simulation. And this is showing in an XY projection of a galaxy cluster within the simulation, all of the tagged globular clusters in purple. So this is calibrated such that by redshift 0, we reproduce the globular cluster mass halo mass relation in these galaxies. We do predict abundances for dwarf galaxies that are in reasonable agreement with observations. So our hypothesis that this perhaps holds into the dwarf regime seems to be pretty good. And very interestingly and relevant to this talk, we predict a self-consistent population of intra-cluster globular clusters that arise in the environments that we tag that are, again, consistent with the few observations that we have of these things. So wonderfully enough, TNG50 also has a catalog of ultra-diffuse galaxies, and these were defined by Jose Benavides in 2023. And they are the subset of dwarf galaxies that reside in the top 5% of radial extent and stellar mass, or at fixed stellar mass, and this is inspired by cuts from Limit-All 2018. And something that we find, or that Jose finds in his work, is that these halos tend to be high spin. So what happens when we probe the globular cluster systems of these guys? So I show on, this side over here, number of globular clusters as a function of stellar mass, and the specific frequency, again, as a function of host galaxy V-band magnitude. All observations of UDGs are shown in the lighter colored shapes in either plots, with normal dwarf shown in darker points. From TNG50, all dwarf galaxies are shown in gray dots, with the circles representing UDGs, and this is consistent throughout the talk. So what we can see is that we actually do a relatively good job, not only reproducing the globular cluster systems of dwarf galaxies within the simulation, but also the UDGs as well. we do have a little bit of an excursion from some globular cluster systems of UDGs in coma, but I was informed at the last conference I gave this talk that these numbers might be a bit elevated. So overall, we actually do pretty good. But more interestingly here is that we don't really find excursions or differences between the globular cluster systems of UDGs and the globular cluster systems of normal dwarf galaxies, which suggests that perhaps UDGs may just be the tail end of sort of radial extent of dwarfs with normal globular cluster systems. Not quite how I wanted to say that, but that's okay. So more interestingly, we can turn now to the kinematics, since we do have these predictions from our globular cluster systems. And we can see in this plot of globular cluster velocity dispersion as function of galaxy V-band absolute magnitude, there's really not a lot of difference, once again, between the kinematics of the dwarf globular cluster system and the UDG globular cluster system, suggesting that, again, these seem to reside in relatively normal dwarf halos. We are able to sort of reproduce a wide range of observations from things that appear to be dark matter free to sort of beginning to reach into this regime of very high velocity dispersion UDGs. But there is a reason for this, and this is small number statistics. Most of these globular cluster systems range between 3 to 5 globular clusters. And so trying to define a velocity dispersion from this gives you a very, very, very large galaxy-to-galaxy scatter, even using very sophisticated MCMC methods to get an estimate of these things. So even with this large scatter, as I mentioned, we're really not doing a very good job at reproducing these things that seem to be consistent with UDGs that reside in Milky Way mass or greater halos. And so me being a theorist, I said, okay, what's wrong? Like, have I really messed up my globular cluster model? Is there something going on here? I'm sad. So I decided to do a mock observation similar to the observations that were conducted by Elisa Taloba to get these points. And since it's after lunch and everyone has a food coma, I would like to invite you to interact a little bit with this talk. So I have mock observations, no, spoilers, mock observations of 8 UDGs that I have selected from within the simulation to fit the criteria of Taloba et al. 2023. And I would like you to guess which ones of these galaxies possess contaminating globular clusters in their field of view. Yeah. Okay, 4 and 6, cool. 5. Any others? Any other guesses? Not quite all of them, thankfully. There is still some hope. All right, so the spoiler slide. So here, any globular cluster that is an actual globular cluster of a galaxy is going to have a blue square and a green point. If it is selected by the same criteria as Taloba et al. 2023, it's also going to have a purple circle. If it is from another subhalo, it's going to have a cyan hexagon. If it's tidally stripped, it's going to have a star. And if it is part of the intracluster globular clusters, it will be a green dot. Now, there is some combination of these points for several of these. So I heard that 4 might have contamination, and in fact, it does not, which is wild. 6 is like our worst case scenario. This field is absolutely terribly contaminated. But what's interesting is if we look at this bottom row, so we see tidally stripped globular clusters that belong to the selected ones here. You have some subhalos here. This guy does pretty good, but this guy has 4 intracluster globular clusters that are accidentally selected in this method. So what does this mean for our velocity dispersion measurements? We're going to get our dynamical masses. So I want to draw your attention to, in particular, S8, the one with a lot of intracluster globular clusters. So we can see that when we just use its actual bound globular clusters, the ones that we know belong to it, it has a very normal velocity dispersion for its stellar mass. But with the presence of interloping globular clusters, we now get a velocity dispersion more on par with that of the Milky Way, about, well, maybe not the Milky Way, but quite massive, about 100 kilometers per second, which is of course kind of wild, but might suggest a failed Milky Way scenario or a failed galaxy scenario if we did not take into account intracluster globular clusters. So let's look at this a little bit more statistically. So if I do this for all of my UDGs and I select the ones where we don't have intracluster globular cluster contamination, we actually do pretty well at recovering the mass. So this is showing mass density as a function of half mass radius or half number radius of the globular clusters. So we can see these orange points tend to reside sort of within the expected NFW profiles for dwarf galaxies. So, around 10 to the 11 solar mass halos. But when we look at the things that do have intracluster globular cluster contamination, we do find a number of objects, even some objects with a number of globular clusters that are selected, that seem to reside in halos that are far more massive, so above 10 to the 12 solar masses. So what would be inferred as, more than the mass of the Milky Way. So looking at S8 in particular, which is highlighted originally if we use its bound globular clusters as a really normal dwarf galaxy, now appears to reside in a halo that's more massive than the Milky Way. So can small number statistics and globular cluster interlopers give us these failed galaxies that are, imposters among us? The answer is I don't really know. So using TNG, we are able to find that this is one potential solution for the sort of enhanced, or not enhanced, but higher halo masses that we find for these failed galaxies. But of course, this is not the only explanation. But I think that sort of in the spirit of sort of talking to observers and wanting to get to the source of what this could be, these failed galaxies could be, I hope that maybe this is helpful in getting proposals. I don't know. This is all I have. Thanks for listening.
So, question for Jessica.
Hi, I wonder if you could take a moment to comment on how you selected stellar particles for assignment of as being globular clusters.
So we don't use star particles, we use dark matter particles. And this is not making any assumptions about, formation. We're not saying they form in dark matter halos. That's something I get very commonly. So it's a dynamical process. So at infall, we select dynamically, so a distribution function type of a selection, dark matter particles that follow a Herrnquist profile. So more concentrated than the dark matter, but less concentrated than the stars, which we believe is true of most globular cluster systems. We toss the halos into their galaxy clusters, let them interact for a little bit, and then we make the calibration at redshift 0.
And so that calibration is based on, may I follow up? That calibration is based on the ages and metallicities of the globular clusters that you observe, and so you assign the simulated globular clusters those ages and metallicities?
Yeah, so we assign the calibration based on tidal stripping. So, as your halos get stripped of dark matter, it should also get stripped of globular clusters. So that's how we're getting the calibration there. And then we do assign masses after the fact to replicate mass functions that we see in Virgo for globular clusters of lower mass galaxies.
That's great. Just quick question. Do you find any trend of the systematics with the number of globular clusters you find and the distance at which they are from the center of the galaxy? Like, if you find more globular clusters away from the center, does that actually inflate your estimates?
So that's something that we haven't looked at in too much detail. The last time I looked at this, we weren't considering interlopers, and for that, no. But with interlopers, I'm not sure off the top of my head, but it would be good to look into.
Hi, Jessica. Michael Hilker here from ISO. So you have shown a case where you say they are stripped globular clusters. Mm-hmm. Is this where the dark matter is also stripped? And in that case, the velocity dispersion was not inflated. Is it just because of the viewing angle? So I think S5 or so, where you have this asterisk, yes, the red one. So there, the velocity dispersion is not inflated by the stripped globular clusters, which you would expect probably in the process. So can you say something when you strip them? When does it inflate?
Yeah, so this is one of only about 4 cases of this happening. And this is the only one of these cases where we actually don't find the inflation. So our thought is that these are probably recently tidally stripped globular clusters. It could also be an error in subfind. So there could be some systematics going on there. So even if you have stripped globular clusters in your sample, there's still hope for recovering the correct dynamical mass.
Okay, so let's thank the speaker again. And the next talk will be online on Zoom. So for the speaker, I won't be able to tell you when, like 2 minutes before. So you have to keep your time.
Yeah, no problem. That's all right. So let me share my screen. Let's see. Please let me know if you can see it.
Yes.
Okay, thanks. So let me start. Hello, everyone. My name is Surud More, and I thank the organizers for this opportunity to present the work of two of my PhD students, Naveen Chaurasia and Amit Kumar, who will be graduating in a few months. Their PhD work focuses on the link between galaxies and their dark matter halos using weak gravitational lensing, in particular related to central and satellite galaxies. So the stellar mass-halo mass relation of galaxies is quite fundamental to our understanding of galaxy formation. This relation and its evolution is essentially an integrated outcome of the galaxy formation process over time. This particular plot from Beruzzi et al. 2010 shows such a relation through the use of subhalo abundance matching. And it shows fairly little evolution of this relation until redshift of 1. And beyond that, you can see the relation changing a little bit. So abundance matching, although it's a wonderful technique, it is an indirect probe of the halo mass and therefore is susceptible to issues, in particular things related to incompleteness, for example. And therefore, one of our aims was to test this relation and its evolution with the use of weak lensing over the redshift range 0.3 to 0.8. So for this purpose, what we did is we used the deep imaging data, which was available from the Subaru HyperSuPrimeCam survey. The depth of the HSC survey allows us to detect low stellar mass galaxies as low as 10 to the 9 out to redshifts of unity, as you can see in this left-hand panel plot. So for the measurements of the weak lensing signal, what we have done is we have used background source galaxies from HSC. So HSC has beautiful imaging with seeing conditions of about 0.6 arc seconds or so in the I band, and these are used to measure the weak lensing signal. Here in the right-hand panel, you see the sky coverage of HSC. So this was from the year 1 data release. Now this area has been expanded at least 7-fold in the internal data release, which is available to us. So the weak lensing signal is related to the tangential shear, which gets imprinted on the shapes of background galaxies due to the matter distribution, which is in between. And when you multiply this tangential shear by the critical surface density, which is a geometric factor related to the lens and the source redshifts, then we can infer the quantity called delta sigma. And this delta sigma is the difference between the surface density averaged within a projected radius r minus the surface density at that particular radius. And so this delta sigma is related to the projected mass profile around galaxies. And so by measuring it, we can get a direct determination of the halo mass as well. So we have used lens galaxies which were divided in multiple stellar mass threshold bins in the 2 redshift bins of interest. And the measured signals are something that can be seen in the 2 plots here. So the lowest stellar mass threshold bin is down here, and the weak lensing signal increases as you go to higher and higher stellar mass threshold bin. So this shows that indeed higher stellar mass galaxies are living in more massive halos. So we model these signals together with the abundance of galaxies in a joint modeling framework using the halo occupation distribution model. And that allows us to get these kind of fits that you see here on in the left-hand figure. So here I'm plotting R times delta sigma. That's why you see the shape somewhat different from what you saw in the previous slide. But you can see that the halo mass only HOD model, it provides excellent fits to our lensing and abundance data. And from this modeling, we are able to put constraints on the average mass of the central galaxies as a function of the stellar mass threshold that we have used in order to measure this weak lensing signal. So that inference is shown here in the bottom plot. So you can see that we get indeed quite good constraints on the halo masses based on our modeling and the observables that we have, in particular the weak lensing signal. So we have also compared these constraints to the constraints on halo masses that you would observe from clustering-based models. And those are shown here with the blue line. And you can see that the blue line sometimes underpredicts, sometimes overpredicts the lensing signal. And that's why it also tends to overpredict or underpredict the stellar mass-halo mass relation. So we have done the same thing for the two redshift bins. And you can see the results here with the shaded bands. So if you use our fiducial abundance abundance measurements from HSC, together with the weak lensing signal, you get the shaded bands. And you see that we get the evolution of the stellar mass-halo mass relation not more than 0.05 dex. So this is pretty consistent with what we get from the subhalo abundance matching methods too, but this is directly measured now using weak lensing. When you turn to weak lensing, because we are using photometric lens galaxies, there are also issues about whether the lensing constraints that we get on the subhalo masses, whether they are robust or not. And this week, just yesterday, there was a paper on the archive with my student where we showed how big this effect can be. And it seems that the bias is quite small, except maybe at the high mass end. Okay, so for more details, you can take a look at that particular paper. So next, I would like to focus on the satellite galaxies themselves. So satellite galaxies, as we know, they reside in dark matter subhalos, which are belonging to big clusters. And what we wanted to do is we wanted to understand how do the environments affect the stellar mass-halo mass relations or the halo masses of these particular galaxies. So the key question was, does the dense cluster environment affect the dark matter distribution around these satellite galaxies? And for this, again, we turn to weak lensing. And the weak lensing signal around these satellite galaxies looks a little bit more complicated. What we have done is we have taken satellite galaxies from the RedMapper cluster catalog, divided them into bins of cluster-centric radii. And then you can see the weak lensing signal here in these 4 different radial bins. The closest to the center is this one, and the farthest away is this one. And then what we did is we compared the weak lensing signals to the weak lensing signal around the control sample of galaxies, which is shown here in red. And what you can see is that in the innermost region, you do see a difference in the weak lensing signals. But as you go further and further out, this difference reduces quite a bit. So we had 2 options to interpret these results. One was that maybe all of these satellite galaxies are experiencing some sort of impact of tidal stripping, and they lose the mass. And that's why these weak lensing signals are lower. The other option is that most of the satellite galaxies look like the control sample of galaxies. It's just that some of them have completely lost their dark matter halos. They have become something like these orphan galaxies, as they are called. And that's why you see a lower weak lensing signal. So in the first case, if you interpret it as just the halo mass difference, then you can see that the posterior distribution of the halo masses of the satellite galaxies is indeed lower if you look at the satellites which are in the innermost regions. They can be as low as factor of 3. But as you go further and further out, you can see that this difference is reducing. But the more interesting thought was what happens if you start to interpret it in this orphan kind of population. So if you say that the difference that we are seeing is because of these orphan galaxies, which have lost completely all their dark matter halo masses. Okay? And so because this model is simplistic, of course, reality will lie somewhere in between. So what we can do is we can only put limits on the, we can only put upper limits on what this orphan fraction is. And this is the upper limits that we got when interpreting the difference in these weak lensing signals. And you can see that in the inner regions, we get pretty like upper limits, which are up to orphan fractions of about 50%. But as you go further and further out, you can see that these upper limits start to reduce. When compared with universe machine, you can see that the universe machine in the inner regions is giving results which are more or less compatible. But as you go to the outskirts, you see that these orphan fractions in the universe machine are kind of over-predicted. And we are trying to understand what the possible issues. So with this, I will leave you with the summary slide. I wanted to tell you with the HSC, we have been able to constrain the stellar mass-halo mass relation and its evolution for the central galaxies in a wide redshift range. And with satellite subhalos, we have put the first empirical limits on what is the prevalence of these orphan galaxies. Thank you.
Okay, so we'll take one quick question.
Hi, it's Kyle Oman from Durham University. It's a question about the last part on the satellites.
Yes.
So my understanding of the orphans, that those are basically just formally unresolved, highly stripped objects in the simulations. And so could you explain maybe what the distinction between a sort of tidal stripping interpretation and an orphan interpretation is, when to me, I don't know, at a glance, it seems like the same interpretation.
Right. Yeah. So the reason why we are putting these upper limits on the orphan fraction is because our model is basically very simple. We say that most of the satellites are not losing anything. They are behave just like their field counterparts, while some fraction are losing their halos completely. This is of course not true, right? In simulations, there will be some subhalos which will, or many of the subhalos will lose some mass due to stripping, right? And so what we are trying to do is just build this particular toy model. And with this toy model, you can see that already the simulations are over-predicting the orphan fractions. Now, what this means is either the subhalos are getting lost due to a lot of numerical effects, which we know that there is some truth to it based on other papers that have looked into this. But there is also a possibility that the models like universe machine, they are putting too many of these orphans in order to explain the clustering results in the small scales or the cross correlation of faint galaxies with really massive galaxies. And so there's something odd going on. And the question is whether these orphans that are put in, are they consistent with our observations? And we can only do that when the orphans are treated in the same manner in the universe machine.
Okay, I think we'll end here. So let's thank the speaker again. And so now we have three lightning talks. So the first one will be online, and then two talks, short talks here in person. So Suchira Sarkar, can you come online? And can we have the presentation?
Yes. Shall I share my screen?
Yes. Yes, you can go ahead.
Okay. So, hello everyone. I am Shuchira, a postdoc from IAU GA, India. I am presenting my e-poster talk on massive disk galaxies with high surface brightness plus low surface brightness stellar disks hosted by Massive Dark Matter Halo, a TNG50 simulation study. So this work is motivated by observations of massive disk galaxies whose total stellar mass is around 10 to the 11 solar mass and which have an inner high surface brightness exponential stellar disk surrounded by an extended low surface brightness stellar disk, which is photometrically decoupled from the inner high surface brightness disk. Now, several giant low surface brightness galaxies, for example, Malin 1, UGC 1382, UGC 1378, NGC 2841, etc., are observed to have such double exponential disk structure. We use Illustris TNG50 simulation, a cosmological hydrodynamical simulation, to find out such double exponential disk galaxies. Here I am showing two such examples out of 8 that we find in the simulation data. The left panel shows idealized synthetic SDSS G-band images of the two galaxies. 2D light modeling done by Galfit on these images, as well as 1D surface brightness profile of these galaxies show that they have a central Sarsic component, an inner high surface brightness exponential disk component, and an extended low surface brightness disk component. Now the total stellar mass, total dark matter mass gravitationally bound to these galaxies are readily available as measured quantities from TNG data catalog. Here I am showing those values in log solar mass unit, and we can see that these values are in good agreement with the corresponding values in observations. For example, the total dark matter particle mass gravitationally bound to the simulated galaxies are 11.94 and 12.27 in log solar mass unit. For MELIN 1, it is 11.9, and for UGC 1378, it is 11.74, as obtained from their mass modeling. Similarly, maximum of the 3D spherically average rotation curve of the simulated galaxies are around 413 km per second and 395 km per second. The flat part of the observed rotation velocity of MELIN 1 is around 400 km per second, and for UGC 1378, it's 282 km per second. So this shows that simulations based on lambda CDM framework are able to reproduce such massive double exponential disk galaxies as seen in observations, and they are hosted by massive dark matter halos. So in our ongoing work that we plan to submit very soon, we have explored various other properties of such galaxies. And if you find this work interesting, please feel free to contact in this email ID, or you can post your questions on Slack. The poster ID is 1475, so you can look up in the poster gallery also. So that's it. Thank you.
Thank you. So can we have the slides, please? So the next presenter will be Richard McDermott.
Hi everyone, I'm Richard from Macquarie University in Sydney. I'd like to thank the organisers for giving me the chance to speak to you today, despite my very tardy reactions to all of the instructions that we had around the posters. So thank you. When we get the slide up, I'll be presenting here. So this poster is based on the MAGPIE survey. You heard about that from Caroline Foster in the first session today. The fantastic thing about the MAGPIE data is that it actually lets us get the same kind of spatially resolved information in galaxy stellar kinematics as we do at redshift 0, but this is at redshift sort of 0.3 to 0.4. So this is really terrific data. It also includes high order kinematic data, so we can use really generalized approaches. And here in the previous slide, you'll have seen we're using a Schwarzschild modeling approach. So this is a orbit superposition method, so we make no assumptions about anisotropy. It assumes traxial shape, so it's a fully generalized dynamical modeling approach. Yeah, this is the work of my recently completed PhD student, Caro Durken, and the paper went on AstroPH yesterday. So this is a little example of the workflow for the Schwarzschild modeling. On the far left top, you see a fit to the stellar image from the MUSE data that we're working with. We take that, we use a multi-Gaussian expansion. This was mentioned earlier as a way of parameterizing the light. We scale this by the mass to light ratio measured from the stellar population. So we're really building a stellar mass model from the MGE. And then we run an exploration of the parameter space, solving for the viewing angles or the intrinsic shape of the potential. We've added a dark matter halo, just a simple NFW halo. And then we allow a sort of a global scaling of the potential in terms of the total mass to light ratio. And then on the far right, you see an example of the kind of data on the top row, surface brightness, velocity dispersion, H3 and H4 kinematics. In the middle, you've got the model that we get from this approach. And in the bottom, you've got the residuals. So really beautiful data and high quality models. And on the last slide, there's some actual results. Yeah, so there's some few takeaways. There's a fourth bonus one if you make it to the poster. Number one is that we find a relationship between the dark matter fraction and the steepness of the total potential, so that galaxies that are very steep and compact for the mass have much lower dark matter fractions than the opposite. In the second one, we find that when we look at the total density slope, it's actually more varied than the stellar slope in itself. And so this argues against the traditional kind of bulge halo conspiracy approach. We don't find really strong evidence of that or any evidence of it. And on the third one here, we do a comparison of a much more simple JAM method, a genes-based method we also heard about in the session, where we don't try to decompose the potential. We just assume it's a single power law, and we vary the slope and we fit for it that way. That was a previous paper by Caro. And then on the y-axis, what we recover from this more general Schwarzschild approach. And we see that this more generalized approach, perhaps unsurprisingly, permits a larger range of total density slopes. So there's arguably more information in these data than just fitting a single power law or a simple Jeans anisotropic model. And there's more about orbital structure. Bottom line is we see the kind of orbital fractions of hot and cold orbits that we see in local samples. We already see this at redshift 0.3. And if you want to know more, grab the link to the paper, check it out on AstroPH, or come and find the poster. Thanks.
And so the last speaker of today will be Nathan Deck.
All right, so I will talk to you just really quickly on the kinematic scaling relations that we've been getting from the Wallaby pilot galaxies. So let's see if we can go to the next slide. That's not the direction. Whoop, and that's definitely not the direction. Okay. There we go. All right, so in Wallaby, we've got about 236 kinematic models that have been half released. So half of them are out already. The other half will be out in a few weeks' time. We're just cleaning it up. And this year is showing one of our nice galaxies. Not all the kinematic models are great for getting out structural parameters, but this one's wonderful. You can find your size, RH1, by where it crosses 1 solar mass per parsec squared. And we've parameterized the velocity by the velocity at RH1 rather than using V flat or V outer. This was just a very strict definition that we can use and apply for all the galaxies. And once you do that, you can go look at your favorite scaling relations. So here we have our size mass relation. It's the best. Everybody loves it. You have a velocity mass relation, much harder, especially it's not studied as much in H1. You have the size velocity relation, which has been studied a bit. And you have something like your angular momentum relation for reasons that we're not going to go into in this amount of time. This is slightly different, but still very interesting. You can see how well we're doing, how our fits are doing. There are some points that are off, and we understand for the most reason why. But like the key point here is that we're starting from the largest sample of rotation curves from a single H1 survey analyzed in the exact same way. We also went and looked at your Tolley-Fisher relations because you have to look at the Tolley-Fisher relations. It's just one of those things you have to do. And again, we get a nice tight fit. This is comparable with everything that you've seen in your favorite Spark sample, Elvis sample, Mighty H1, whatever you want to pick. This is certainly comparable to it, perhaps with slightly tighter scatter at this point. Once we get the full Wallaby sample in place, it's going to look much, much better. But this is sort of where we're at right now with these scaling relations, just giving a nice starting point and a taste of what you're going to get with Wallaby and just how we can go about doing this in a very rigorous fashion, robust fashion, really drilling down into the uncertainties that we can do with this sample. And that's it for me.
Okay, so thanks everyone for being here. There were no questions for the last 3 presentations. So if you have questions, go talk to them either in person or on Slack. And we will reconvene in a bit less than half an hour, 3:30.
Ils ont des places, donc, comme descendre, on est appelé,
Surtout quand théoriquement, il y a des posters en même temps.
voilà, c'est ça.
Après, les posters, tu peux les regarder en ligne, PDF, c'est peut-être plus simple. Yeah. Yeah. Yes. Maybe I will just stay here to check with them. Yeah, okay. Perfect.
Somewhere. Right. There's never enough time of the day.
Now, then we can apply for the document. It's not a game.
Sharing
Yes.
the next one on
Consistency.
for questions and stuff.
Yes.
Do you want to take the mic around or would you like me to take the mic around?
I don't have anything.
That's fine, that's easy. Easier.
Yeah,
Because
like,
you
I
have
say
to have
things,
it,
yeah,
yeah.
exactly.
I did
So-
ask them if they had another mic, but no, so unless you use those.
Yeah.
Which would be fun.
Yeah, okay.
Yeah.
So,
Just
we're all in
don't,
person.
yeah, just don't do what job stand in front of the speaker.
Okay.
Because they have to turn the mic off when you stand in front of the speaker. because
Okay,
you'll get
so I
feedback.
can stand on the
yeah.
platform or just
Well,
stand
to
here.
the
at
side of
front.
it, to the side of it.
Okay, but just not literally in front of the.
Yeah,
Okay, great.
there's just a one way when you get that and it's like, yeah.
Yeah, I don't know if people will try to keep them to write down on the buttons.
Yes, no, I'm just saying to Gary, probably brief them.
Yeah, but if not everyone's like here immediately, but I'll try to, I know some of the people, I don't know if I know the other folks. They'll be able to try to.
Actually, what I might say is. Go to remote, slap on instructions on which buttons.
That would be amazing.
Yeah.
Probably do that.
Probably didn't know what to make there.
Oh, yeah, because I mean, like, it's doing
Yeah.
this, and then they need to the first couple of people on to go over to the second one. With that in mind, that's what they're trying to create, and so you don't really expect that many deviations from that. But, so there's some reason to overlap between, you know, we wanna focus on the ideas.
So that one.
Yeah, so these are the unique and galaxy clusters that I compared to.
Hello. Hello. I don't know if, so I hope stragglers come in quickly because we're just going to get started in the interest of time. Make sure we can get through everything. I am delighted to introduce our first speaker for this session. Federico Lelli is going to be telling us about dynamical scaling laws, rotation-supported galaxies. Hopefully get the slides up shortly. I'd like to, everyone online, please, if you can, put the questions onto Slack. That's really easiest for us to monitor and also interact with after the fact. Okay, take it away, Federico.
Good afternoon, everyone. First of all, I would like to thank the organizers for inviting me. I'm going to discuss the dynamical scaling laws of rotation-supported galaxies, but let me start with the big question. What's dark matter? Of course, there are many possibilities, many theories, but in the end, it really boils down to two possibilities. One is either a new particle that doesn't interact with baryons or only weakly, and so the standard model of particle physics is broken and needs to be extended, or we need new dynamical laws, and so gravity is broken and GR needs to be extended. So I think as astronomers, we really have this exciting possibility to constrain fundamental physics much better than the physicists. So we should be very lucky, we should feel very lucky to be working on galaxy dynamics in this day and age. So my approach to the problem in this talk will be to focus on empirical laws that describe galactic rotation. So on relationships that are independent of any dark matter model or cosmological model or modified gravity model that you may think of, but that just emerge from the data. And so they hold true independently of our biases or preferences. And I will describe 4 of them that are written here. We have been reviewing these empirical laws in a number of contributions recently. There is a paper by Stacy McGove written for the IAU Symposium 353. Then there is a short review I wrote for Nature Astronomy a couple of years ago. And there is another review that I wrote for the IAU Symposium 379, which is a bit more technical and pedagogical in nature. So if you want to know more, you may have a look at these papers. So let me start with the first law, which is flat rotation curves. I mean, this may sound obvious and well known to many of you. You just add the dark matter halo and you get a flat rotation curve, but it's really not, because the flat part of the rotation curve is given by the quadratic sum of the baryonic contribution that is declining and the dark matter contribution that is rising. And so to get a flat rotation curve, the two components must know about each other in the sense that as the baryonic contribution decreases, the dark matter contribution must increase by a precise amount in order to keep the rotation velocity flat. And this was called Discal conspiracy by Van Albade and Sanchisi back in 1986. And they actually wrote, luminous and dark matter seem to conspire to produce the flat observed rotation curves in the outer regions. It seems unlikely that this coupling results from the large-scale gravitational interactions between the two components. And this is still a problem for lambda CDM today. For example, there is a recent paper by, well, not that recent anymore, but a very good paper by Desmond in 2017, in which he used a quite general model in lambda CDM to associate halos to galaxies. And one of the findings is that the rotation curves that you get from the model are not as flat as the one that we observe. So understanding flat rotation curves is still a problem to the present day. Now, remarkably, there is a recent result by Mistele and collaborators in which we use weak gravitational lensing in order to trace the gravitational potential all the way out in galaxies. I don't have time to enter in details, but I will just say that Tobias Mistele has derived an exact analytic formula in order to infer the gravitational acceleration directly from the weak lensing measurements, which are this delta sigma shown over there, in spherical symmetry. So applying this formula, one can infer the run of the circular velocities versus radius. This is a plot that shows in red the H1 rotation curve from a typical galaxy, and then the weak lensing measurements that comes by stacking thousands and thousands of galaxies. So it's a statistical measurement. And when we focus only on isolated galaxies, selected to be isolated, so we are tracing the potential of the galaxy, not of the environment, we get that rotation curves appear to be flat all the way out for hundreds of kpc, possibly up to 1 megaparsec. So empirically, what we get is the gravitational force goes down like 1 over r, not 1 over r squared. That's just what we get from the data. Now let me move to the second law, which is the baryonic-Talley-Fisher relation, which is important because it tells us that this flat rotation velocity is not some random number that can vary from galaxy to galaxy, but is actually very closely related to the baryonic mass of the galaxy, the sum of stars and gas, even though the flat rotation velocity comes from the dark matter-dominated region of the potential. So it's not a trivial relation to understand at all. Another important point is that the baryonic-Talley-Fisher relation has a slope very close to 4, so you can write it down in this way, and the normalization by simple dimensional arguments, just using dimensional arguments, can be written as 1 over the Newton gravitational constant times an acceleration scale. In other words, the galaxy here are defining a characteristic acceleration in galaxies, which is unavoidable. It just comes from a slope very close to 4. And if you fit for it, you get a value of the order of 10 to the minus 10 meters to square arc second. Another important point is that the scatter is very small. It's actually consistent with the observational uncertainties, so the relation may be intrinsically thin. Second, there is no residual dependency on things like effective radius or gas fraction or morphology or things like that, as far as we can tell. So if we know only the baryonic mass, we can get the flat rotation curve in the outer parts. And finally, this is a fine-tuning problem for lambda CDM in general, independently of what model you are using. Because in lambda CDM, you expect a relation like this, where the baryonic mass goes as the rotation velocity along the flat part with a power of 3, multiplied by the baryonic fraction of the galaxy, which is basically the ratio between baryonic mass and dark matter mass. If you assume that this baryonic fraction is equal to the cosmic value, so omega baryons divided by omega CDM from the CMB, for example, you get this dash line, which is clearly off from the data in terms of both normalization and slope. So in order for the galaxies to be on the observed position of the baryonic-Talley-Fisher relation, what happens is that a halo up here must know exactly how many baryons to hide or to expel in order for the galaxy to end up in the right position of the baryonic-Talley-Fisher relation. And this must happen systematically as we go down in baryonic mass not in a constant fashion, but in a relevant fashion in order to turn a slope from 3 to 4. So it's a fine-tuning problem. You need to have a model that necessarily gives a baryonic fraction that varies systematically with V flat or baryonic mass in a given way and with basically no scatter. Now, it's important to address the question of whether there is any galaxy deviating from the baryonic-Talley-Fisher relation. If you go through the history of this subject, which is more than 20 years old, you may infer a sort of golden rule, which is that as the data quality increases, the scatter around the relation decreases, and the outliers tend to disappear. Now and then there are claims about galaxies deviating from the Talley-Fisher relation. One of the most recent ones are ultra-diffuse galaxies. I looked at this in some detail, and there is a paper today on the archive that has just been accepted on ANA letters, in which I show that UDGs, which are these plots, these points here in blue, indeed deviate from the baryonic-Talley-Fisher relation, but exactly in the same way as any other normal galaxy that is face-on and has relatively low quality data, and that we usually drop from our measurements because of quality assurance from some basic quality cut. So my take here is that there is nothing special here, it's just having face-on galaxies with low quality data. Now let me move to the next law, which is the central density relation. This is broadly related to the concept of rotation curve diversity, but actually I prefer to talk in terms of regularity rather than diversity. So have a look at this plot here. Oh, sorry, I didn't want to skip, but okay, let's focus on the left panel. These are just rotation curves from the Spark database, color-coded by the effective surface brightness of stars. So what you see here is not diversity. What I see here is a remarkable regularity. There is an organizing principle in galaxies by which, if you are a low surface brightness galaxy, you tend to have a slowly rising rotation curve that reaches the flat part in the outermost region, whereas a high surface brightness galaxy rises steeper to the outer region. And in the extreme case of the most high surface brightness system, we actually cannot even see the rise. They are already flat within 1 kpc. This can be quantified. You can measure the inner steepness of the rotation curve and then plot it versus the central surface brightness of a galaxy. And what you find is a nice scaling relation that tells you how steep a rotation curve gets to the flat part based on its stellar surface brightness. So this is again regularity, not diversity. Now, another way to quantify this, which is more physical and elegant, if you like, is to use a formula from Tumre in 1963 that gives the central dynamical surface density of a disk just by taking an integral of v squared over r squared. So this is a way to quantify the inner steepness, but in a more dynamical way. And so we can write things down in solar masses to parsec square. And we can plot it against the baryonic surface density within a similar aperture of the rotation curve data. And we find that there is indeed a nice scaling relation extending for 5 orders of magnitude that applies to the central galaxy region. This relation is now nonlinear. So there is a slope of about 1 in the top part. And this is the regime of high surface brightness galaxies that are baryon dominated in the center. So this is the region where baryons dominates and the baryonic surface density is equal to the dynamical surface density. But then there is a characteristic surface density scale in the problem that comes out from the data. And below this critical surface density, galaxies start to be dark matter dominated all the way down to the center in the conventional way. So these are the low surface brightness dark matter dominated galaxies. Now, a characteristic surface density can again be turned into an acceleration scale just by multiplying over Newton constant. Or if you are a physicist and you put g equal to 1 in natural units, then acceleration and surface densities are the same property. And again, you get a number of 10 to the minus 10 meters to square arc second. This relation also has more scatter, as far as we can tell, is consistent with uncertainties, and it has no residual dependencies on other properties like stellar mass, gas fraction, and so on, which is quite weird from a dynamical point of view for reasons that I don't have time to explain, but feel free to ask me. Now let me move to the last relationship, which is to some extent the most general of the 4, because it deals with spatially resolved data. So now in this plot, every point is not a single galaxy, but is a radial element in different galaxies. So on the y-axis, we have the observed centripetal acceleration, v squared over r, where each point comes from one spatially resolved element of the rotation curve. While on the x-axis, we have a similar quantity, but computed from the baryonic distribution. So it's the baryonic gravitational field that we can measure by solving the Poisson equation for the given distribution of stars and gas. What you see here is, again, a very tight relationship covering several orders of magnitude. Again, it's not linear. There is an explicit acceleration scale in the problem that just emerged from the data, and is again of the order of 10 to the minus 10 meters to square arc second. When you are above these critical acceleration scales, the data are along the one-to-one line, so g ops is equal to g bar. These are regions that are conventionally dominated by baryons, and they are found mostly in massive spiral galaxies, which are color-coded in red here. When you go below this acceleration scale, the points deviate from the one-to-one line, so this is dark matter-dominated regime, but it's important to distinguish 2 different regimes. There are the outer parts of spiral galaxies in red, but there are also the inner parts of low surface brightness dwarf galaxies, and they end up being on the same position of the relation, which is highly non-trivial. Again, scatter is small. We cannot tell whether there is an intrinsic scatter at all, and there is also no other dependency either on global properties like total stellar mass, total baryonic mass, whatever, or local one like local surface density of stars or I don't know, orbital frequency or anything you can measure at different radii. And this tells us that there is a local coupling between baryons and dark matter, meaning that if you know the distribution of baryons, you can solve the Poisson equation, get G bar, and then predict the full shape of the rotation curve or vice versa, with an accuracy that is driven by the observed scatter that is of the order of 30%. So if you think about that 30% in astronomy, it's amazing. Now, it's important to understand that galaxies are on the same radial acceleration relation despite their diversity, because galaxies are diverse, but they end up on the same relation. So I'm showing 3 examples here. On the left is a bulge-dominated spiral galaxy, where the bulge component dominates in the inner parts and gives this declining rotation curve in the inner regions, then gets flat. This is a high acceleration system, high density system, so it covers the high acceleration parts of the relation and then starts to deviate from the one-to-one line when you hit the dark matter dominated regime. In the middle is a disk-dominated galaxy that already shows some level of mass discrepancy in the center and tends to cover intermediate acceleration ranges by going on top where the other galaxy ends. What I mean here is that the relative amount of dark matter in the outer parts of this galaxy, which give this amount of discrepancy from the one-to-one line, is equal to the relative amount of dark matter in the more central parts of another galaxy, despite the 2 galaxies, of course, don't know about each other. But this depends on the local value of the baryonic gravitational field. And when we go into the low mass, low surface brightness regime, this becomes even more extreme in the sense that these are low acceleration objects, low density objects, in which the mass discrepancy is high everywhere, and the amount of mass discrepancy that you have in the inner part is comparable with the amount of mass discrepancy that you have in the outer parts of a typical spiral galaxy, and they all end up on the same scaling relationship. So basically we have 3 scaling laws, but 1 acceleration scale, despite the acceleration scale play a very different physical role in each one of them. So in terms of the baryonic-Talley-Fisher relation, this acceleration scale sets the normalization of the relationship, which is related to the global ratio between baryons and dark matter across galaxy, how MB over dm varies across the galaxy population. In terms of the central density relation, the acceleration scale sets this critical surface density that determines the transition from baryon to dark matter dominated galaxies in the central parts. It's a very different regime from the baryonic-Talley-Fisher. And finally, the radial acceleration relation has an explicit acceleration scale that tells us the transition from baryons to dark matter domination within each galaxy, at which radii in a given galaxy dark matter starts to dominate, right? And so this is, to me, very puzzling to understand in the general framework of galaxy forming within dark matter halos by completely random and stochastic processes. There is clearly a quantity, which is this acceleration scale, that plays a critical role. And all this was actually remarkably predicted by Milgrom in 1983, more than 40 years ago. The predictions are written in the abstract, so you don't need to read the whole paper. But actually, I will suggest you to read the paper because there are many remarkable things that one can learn. But I will stop here and just say these are empirical relationships that needs to be understood independently of whether we think dark matter is or isn't. Thank you.
Thank you, Federico. So questions?
Thanks, Federico. This is Barbara Catinella from UWA. So you showed that the shape of rotation curves depend on surface density, and I agree that it's a similarity more than diversity. But of course, it depends also on stellar mass, on galaxy luminosity. So what's the fundamental parameter and why, in your opinion?
Yes, so as far as I can tell, if you look at the inner steepness of the rotation curve, so the inner part, then surface density, in particular stellar surface density that dominates there is the dominant parameter. There is also a correlation, of course, on stellar mass, because stellar mass correlates with surface density, but that is less strong. But then if you go to the outer parts, along the flat part, the only thing that matters is the baryonic mass. So this is well established, the residuals around the Talley-Fisher relation, if you measure the flat part, do not seem to depend on effective radius, surface brightness, and so on. So there are two different regimes that work in a different way when you go from the inner to the outer parts.
So the next question coming from Slack. So Sarhoud Moore is excellent talk. I had a question. Can you comment on how the weak lensing results contrast the falling satellite velocity dispersions as a function of radius inferred with SDSS and maybe other results? Any ideas as to why the two could differ?
So I'm not sure I entirely got the question, but I had a slide that looked in that in more details, but now it's gone. But anyway, I guess what I can say is that in that paper, the equation that was derived by Tobias Mistele has been applied on strictly isolated galaxies. And in particular, we selected galaxies that don't have any other satellite within 4 megaparsec. Satellite being something at least 10% the mass of the central galaxies. So these are extremely isolated because the idea was really to measure the gravitational potential of the galaxy and not the potential of other things around. So I presume that different works apply different selection criteria, and if you don't select galaxies that are strictly isolated, you may get different results.
Okay, so Sarhoud is following up. Apparently there are similar isolation criteria applied, but maybe this is a longer question you can clarify later.
Yeah, okay, I will reply on Slack.
Yes, the similar isolation criteria are also applied in papers like these. So, okay, so next question from
Yeah, thank you. I was wondering about the RAR. I saw that there are some recent results of people that say that in something like 20% of Spark, you have hooks in the RAR that are in principle not expected within the MOND framework, but they claim they are sort of a natural outcome with CDM simulations. I was wondering if you can comment on that.
Yeah, so one thing that one can do is to actually assume the average RAR and then fit galaxies. So this is equivalent as fitting MOND to a galaxy, essentially. And in that, you can play around with distance and mass to light ratio and inclination within the uncertainties in order to give more freedom to a galaxy to be in the position of the RAR. And when you do that, many of these hooks disappeared, and the scatter around the relation goes down to 10%. So in other words, this means that if you optimize some nuisance parameter that we only know within some uncertainties, then the scatter around the relation could be as small as 10%.
Okay.
So the short reply is that it's probably observational errors.
Okay, so I saw a number of questions. I'm not quite sure who went first. I'm going to ask number 4. Sorry, Kyle.
Thanks. So, Federico, you pitched the BTFR as sort of a fine-tuning problem. Another way to look at the same fine-tuning problem is, okay, galaxies don't have random properties, right? Their sizes and their masses correlate with each other. There are many scaling relations in galaxy formation. And so you can look at it as, why doesn't a galaxy form with a random size? It forms with the particular size that makes it land on the BTFR, for example. And, that, I guess, has something to do with self-regulation processes in galaxy formation. And now I'm losing my train of thought, but do you have do you want to pick up on this and
Yeah, so I mean, the problem that I find particularly compelling is that galaxy formation in lambda CDM is an entirely stochastic process. No, you have the merging of dark matter halos, then you have gas inflow, star formation, supernova feedback, AGN feedback, gas outflows, reaccretion, something entirely stochastic. And so you would rarely expect to have relation with extremely small scatter, especially when they connect a baryonic property with a dynamical property. So what it means, for example, in terms of the baryonic Talley-Fisher relation, is that the baryonic fraction, which I mean the fraction of collapsed baryons, cold gas and stars, over the dark matter mass, must end up being the right one with an accuracy of 20% or less, despite all this stochasticity, right? And that's, to me, is a fine-tuning problem.
Okay, so we're going to take one last quick question. Sorry, Luca, if you can follow up later.
Thanks. Nice talk, Federico. So I guess my question goes on a similar line to Kyle's in the sense that you were talking about the baryonic telefish relation and the fine-tuning issue. But as far as I know, it seems that a lot of simulations get managed to reproduce the baryonic telefish relation. And they use different subgrid physics, different, et cetera, et cetera, et cetera. So I'm wondering what your thoughts are on that. So how come all of these different models that use different kind of subgrid physics, et cetera, still manage to reproduce that?
I think this goes in line with what I'm saying. You can use completely different model to the parameters, get the right result, but you don't necessarily learn something physical because you are doing a fine-tuning exercise that is getting the right slope. What I find more difficult to understand, and I think we will understand with future survey like Wallaby and then the SK, is whether there is really an intrinsic scatter around this relation, right? Because in any model that you can imagine, there must be some intrinsic scatter if this is a relation that emerged from the galaxy formation process. If it's a natural law, like the third law of Kepler, then you expect zero scatter. So the scatter will be the key to distinguish between the two between the big question, the two possibilities that I started with.
Okay, let's thank Federico again. And our next speaker is Pavel Manzara-Pina, and he will be telling us about an ultra-deep and ultra-sharp view on gas-rich, ultra-diffuse galaxies, a population-defying CDM.
I shortened the title a bit now for the talk. So yeah, hello to everyone. Thank you very much for being here. I'm Pavel Manzara-Pina. I am a Benning Fellow at Leiden Observatory. And indeed, I will be talking today about an extreme population that I think seems to be challenging CDM. How did we say I go through this? Thank you. So as we have seen already with the great talks by Luis and by Jess, UDGs are these ultra-diffuse galaxies, and are characterized by having very large effective radii, while also having very low surface brightness. And what this means is that at fixed stellar mass, UDGs are those dwarfs that have the largest distribution, the largest stellar mass distribution. And because of this, they have extremely low stellar mass surface densities, which make them very diffuse, very hard to detect, and they remain a fairly unexplored galaxy population. Now, you can find UDGs in all different environments, and I was particularly interested in those UDGs that are in isolation. So in particular, a few years ago, Gluck-Lisman and collaborators found around 120 galaxies that can be classified as UDGs according to photometry from SDSS, but they also have an H1 counterpart from the Alpha H1 catalog. And they found that they are heavily they are isolated and they are heavily gas dominated, as you can see here in this plot that shows how for a typical stellar mass of 10 to the 8 or below, so they are really dwarfs, they have as much H1 as the Milky Way. So they are heavily gas dominated, and they also seem to have narrow velocity widths, which suggest low rotation velocities. So over the last few years, we have tried to understand better the kinematics of these galaxies, and by obtaining, at first, mid to low resolution observations, we found that indeed they have these beautifully rotating H1 disks. And I'll show you here 3 examples. We have done the kinematic forward modeling to really understand their intrinsic properties, and I'm happy to give you more details about this kinematic modeling if you're interested. But for now, I want to focus on one of the first results we found that was highlighted just now by Federico, which is the fact that these ultra-diffuse galaxies appear to deviate from the baryonic Tully-Fisher relation. Now, I did my PhD at the University of Groningen in the Kaptein Institute, and when you arrive to the institute, they give you a desk and they give you a pile of PhD theses for the last 40 years that essentially have all of those measurements. So finding something that is not on the Tully-Fisher relation was quite upsetting for us, and we have been trying to put the galaxies back on the relation by thinking of different systematics. The most obvious of them is the inclination, but also non-circular motions, and a few others I'm happy to discuss with you. And we didn't find any convincing way to put the galaxies back at the relation, all of them. When you look at the data, it's just obvious, I think, that not all of them are phase-on galaxies. These were these systems with mid-resolution H1 data, and I just want to emphasize that these results seem to be supported at this point by about 100 ultra-diffuse galaxies that have unresolved kinematics, so with a grain of salt, but still, and with a handful of more UDGs by different groups with resolved H1 data, and all of them seem to suggest that as a population, these ultra-diffuse galaxies deviate from the Tully-Fisher relation. Now, I found this quite interesting for a number of reasons related to galaxy evolution, but I think that the first implication that was very clear for us was that this suggests that compared to other dwarf galaxies, these systems must have atypical dark matter distributions. But to really go into the detailed dark matter distribution, we need better data. And because of this, we have started an observational campaign to obtain very deep optical imaging of these galaxies and also high resolution H1 data, which is crucial. So today in this talk, I will present you the results for 3 of these galaxies for which these data are ready, but hopefully there are a few, at least a few more to come. So these are the 3 galaxies that I will be talking about today. You can see there the optical images. You can see there some of the properties. So 2 of them are at 8 megaparsecs according to the H1 redshift. 1 of them is at 30 megaparsecs. They have different inclinations, low inclination, high inclination, intermediate inclination. The 3 of them are heavily gas dominated, so 95% of the mass is in the form of the H1 gas. They are extended because they are EDGs. And they have different offset with respect to the Baryon-Tully-Fisher relation. So the one on the left is very, very far away. The one in the middle is in between the Tully-Fisher and the one on the right. And the one on that side is still off, but is closer to the other 2. So we have obtained deep H1 imaging for these galaxies using the VLA and Meerkat. And I showed you here the 3, if you ask me, extremely beautiful H1 maps, velocity fields for these galaxies that show the clear pattern of a rotating disk with very ordered rotation without strong non-circular motions. And you can see also there that they are not only phase-on galaxies. And what I show you there in the 3 panels are the kinematic parameters that we have derived with the forward modeling technique, in particular with 3D Barolo. So what you can see is in blue, the velocity dispersion of the gas that has the typical values that you see in star-forming dwarf galaxies. In red, the rotation velocity of the gas. And then once you correct the rotation velocity for the pressure-supported motions traced by the velocity dispersion of the gas, you end up with a circular speed, which is shown there in gray. And that's really the parameter that we want to look at because it's the one that traces the gravitational potential, right? So we're going to use a technique that has been there for at least 40, 50 years. And as you know, the idea is to explain the observed kinematics of the galaxies with the contribution coming from the gravitational potential provided by the baryons, so the gas disk, the stellar disk, and then the dark matter halo. Now, for a dark matter halo, you need to assume a functional form. And because we know that many dwarf galaxies have cores, we are using the so-called core NFW profile. And this is essentially the NFW that we all know very well, but it has an additional parameter that allows the fit to develop a core if that fits the data better. So I will show you now the results for the mass models for these 3 galaxies, and are these 3 here. So what you can see is in blue, the contribution from the baryons, in black, the best fitting dark matter halo, and in red, the overall, the total mass model compared to the observations that match quite well. So I list here the observational parameters, and the point that I want to emphasize is the extremely low concentration parameters. It was a bit too quick before, but the concentration parameters are between 1 and 4, which means concentrations between 4 to 8 sigma below the expectations in CDM. So another way, and I should emphasize this, so these are low densities also in extended scales. And another way to visualize this, considering that depending on which type of dark matter halo profile you are fitting, the definition of the concentration can change, is to think instead of Rmax and Vmax, where Vmax is the maximum circular speed of the halo and Rmax is the radius at which Vmax happens. And what characterizes these low density halos is that for a fixed set Vmax, compared to the overall dwarf galaxy population, Rmax is much higher. So they are very low density halos. And you can see that the low densities extend to very large scales, 10 or 20 kiloparsecs. These halos are so extreme that I will argue represent a problem for CDM. And the way in which I will visualize this is through this plot that we have seen already a couple of times today. So it shows on the y-axis the circular speed of the dark matter halo measured at 2 kiloparsecs as a function of the maximum circular speed of the halo. And for reference, I'm showing in gray points that come from a cosmological simulation using CDM, and the color points there are the measurements for these ultra-diffuse galaxies. So obviously they don't match, but also we know that in principle, it's not fully unexpected because dwarf galaxies have cores, right? So stellar feedback could lower these densities. But I will argue that the stellar feedback is not enough to reproduce those galaxies. And to illustrate this, I show you here now in purple a set of dwarf galaxies with high resolution kinematics for which I have derived the mass models in the same homogeneous ways. And you can see that those galaxies that have cores indeed have lower densities, lower densities than you can see in CDM, but they don't really get to these values. And I want to emphasize that these galaxies here that I more or less enclose with this purple circle, most of them have, when you look at the size of the core, they have cores as large as is in principle allowed by galaxies, just based on the energy available from supernovae. So going below this, I think, is quite challenging, and that's why I made a claim that these galaxies are difficult to understand in the context of CDM, because feedback cannot lower the densities that much. Now, if baryonic physics cannot do the job, it's worth to ask whether alternative dark matter models can do it. And a particular dark matter model that was quite interesting for us is self-interacting dark matter. And the reason is, well, as you know, in general, it's a successful model, at reproducing the rotation, the diversity of rotation curve problems that Kyle was introducing before. And the reason for this is because the self-interaction between the dark matter particles lead essentially to a gravothermal evolution of the halos. So depending on the initial properties of the halos, you can find, and when you observe them, you can have halos that are very cuspy or halos that have developed huge cores. And again, this is just because of dark matter physics without the need for stellar feedback. So we wanted to see if this type of halos for these ultra-diffuse galaxies could be reconciled with the idea of self-interactions in the dark matter particles. And actually, it looks like this is the case. So the plot on your left is the same that we were looking at before, but now the plot at the right is analogous to it, but the blue points are now the results from a simulation, cosmological simulation, where the self-interacting dark matter particle is considered. And as you can see, I mean, for the classical dwarfs, this is not a problem. I mean, you see that there are a bunch of blue points here. So SIDM can produce the low densities we observe in classical dwarf galaxies without much problem. Thank you. But what I find extremely exciting is to see that now, close to our ultra-diffuse galaxies, there are also a bunch of dark matter halos in the simulation. So while CDM seems to struggle to produce these low-density halos, even with stellar feedback, they seem to be a natural outcome for self-interacting dark matter. And with this, I come to my conclusions. And I think the main points to take away are that at least some ultra-diffuse galaxies seem to be outliers of the baryonic-Fisher relation. I think I have made peace with Federico that we're going to agree to disagree at this point. And those galaxies for which we have the best H1 data, for them we find that they have dwarf-like halo masses. This was not given because, as Luisa was mentioning before, a potential idea is that some of these galaxies are sort of failed Milky Ways. So at least for this tree, we find dwarf-like halo masses. The thing is that these halos are extremely low density, as I was saying, seem to be inconsistent with CDM plus feedback, but instead they seem to be more naturally explained in the context of self-interacting dark matter. So thank you very much. I'm happy to take questions.
I think we'll start here.
Thank you for the talk. So my question is about, this is self-interacting dark matter in absence of feedback, right? What do you think how do you think feedback would affect that? Do we have any simulation happening now?
Yeah. Well, so in fact, these results that I was showing are only for, I will get there at some point. Maybe I will not get there, didn't I put it? It was there. You can ask Victor more, of course, about this, but so the simulation that I was showing are for self-interacting dark matter only, so that it doesn't have feedback, but at least what some simulations have shown, and you can see this in this plot that shows on the vertical axis, essentially the inner slope of the dark matter halo as a function of stellar mass, is that compared to CDM, the effect that feedback has on the halos is much less than in self-interacting dark matter. And it does sort of make sense, right? Because you already lower the potential because of the self-interactions. So answering your question in short, as people have shown in simulations, the impact of feedback is much weaker, especially for UDGs that have a very extended baryonic distribution.
Okay, so
could these be tidal dwarf galaxies?
Yeah.
There are many examples of tidal dwarfs.
Absolutely. That's a very interesting question. Among the pile of theses that you get when you do the PhD at Captain is Federico's thesis. And Federico had found a bunch of tidal dwarf galaxies that deviate from the Tully-Fisher relation. I don't think this is the case, mostly because of the completely different environments in which the galaxies live. So we know that tidal dwarf galaxies live still close to the progenitors, while these galaxies that I was just showing you are selected to be isolated. So I think that's the main. I wanted to show you a slide, but it will not come here. This one here. So that's what I was showing, that the tidal dwarf galaxies that we know deviate from the Tully-Fisher relation are in completely different environments, while ours are isolated. And also those tidal dwarf galaxies are expected to be dark matter free completely, while for some of these ultra diffuse galaxies, we do find that they have some dark matter.
Okay, we'll take one last question. I apologize to the others. I hope we can follow up on Slack and later in person.
Hi, Eric Tyler at Space Telescope. This is really neat, but I'm missing something here. Excuse me. It looked to me like you didn't quite get to the point where the rotation curves turned over to flat. So how can you constrain the concentration and the total mass when you're not reaching the flattening?
No, I think we're pretty much reaching the flat part for some of them. So, well, yeah. I mean, you can see here. I mean, essentially, the gradient of the flattening is really weakening. The other thing take into account that's essential, even for these low concentration halos, when you go to 10, 20 kiloparsecs, I don't think there is really much chance to keep growing much farther away. So that's why we managed to get these constraints on halo mass and concentration.
Okay, let's take our speaker again.
Yeah, thank you.
So our next speaker is Zara Basti. She's going to be telling us about calibrating mass modeling methods with numerical simulations of galaxies.
This is a line summary and this is forward? Yes. Okay. We get the slide.
Okay. Okay. So, hello everyone. I'm Zara Basti from Queen's University, Canada. And first of all, I want to thank all committee members who made it possible for me to be here today and talk about this work in our group about calibrating mass modeling techniques. So, okay. So, first of all, we know dark matter is there. I think that's why we are all gathered here today for so many reasons. CMB, gravitational lensing, rotation curve, and so on. And we know it's a complicated problem. And to answer that, I think it's fair to say the best framework to study that is galaxies. But galaxies, as you can see here, are super complicated system. It's not like that we can model them pretty easily. Everything's all over the place. So it's a complicated problem. And to understand how dark matter is distributed within this complicated system, we have to do some modelings. This is a model. A very minimal simplification of the previous slide. So we usually assume that there is a bulge, there is a disk, and all over the place there is dark matter halo, and each of these components will follow a specific function, usually an FW for the halo, and so on. And our approach usually to get the dark matter mass distribution is that we have access to the total mass using dynamical tracers, i.e. rotation curves. And we also have photometric images for mass, for stellar distribution and gas. So comparing the two, we could get dark matter distribution. However, there's a catch. We have to make so many assumptions. We have to make assumptions. Oh, sorry. The previous one. Okay. So we have to make assumptions about mass to light ratio and non-circular motion, and our sampling issue, structural assumption, and so on. And why we care so much about dark matter mass distribution? Because dark matter mass distribution is in fact the only accessible characteristic of dark matter. So we better get it right. Otherwise, all our understanding about dark matter is flawed or biased based on the distributions that we got. So the important question that we have to answer is, using common mass modeling techniques that are very common, everybody use them, how far from the truth we are, or simply how accurate we are in terms of getting true dark matter distribution. But this is not a simple question to answer, because within the universe, we don't have access to the ground truth dark matter distribution, right? And because of that, we approach this problem using simulation, because within the framework of simulation, we have access to everything. We have access to particle phase space at all times. So if we go ahead and apply common mass modeling techniques on simulation data, assuming that we are an observer, and then get the dark matter profiles we get and compare them with the ground truths from the simulation, then we can see how off we are. And for that, we have used, Nihao simulation, which I really want to thank them for granting us access to this wonderful piece of work. And here's the kind of, I keep messing with this. So, and here's the kind of data that we get from the Nihao simulation as our ground truths. For example, this is surface brightnesses for gas and stellar component, and this is the circular rotation curve for this component directly extracted from the simulation. This is our ground truth data. But before getting to our methodology and approach, I want to set the terminology and introduce our sample. So from Nihao, we had access to about 100 galaxies. And in those 100 galaxies, we set two criteria. First of all, we only took galaxies that had a stellar mass larger than 10 to the 9 solar masses. And also, we wanted to only consider this key system. And so for that, we checked flattening of all these galaxies and made sure that the flattening of the stellar disk should be lower than 0.4. And for most systems, it's less than 0.3, actually. So that is the sample. We ended up having 33 galaxies, and we also oriented all our galaxies to be edge on. And that is because we want, when I want to say rotation velocity, that's same as line of sight velocity, which is usually extracted through Doppler shift. And whenever in this talk I say circular velocity, I mean the velocity that is extracted from the gravitational potential. That being said, we go to our first method. We use this method. It's the common velocity decomposition method used by astronomers. I'm going to call it the velocity space. And the way it happens is that we get the rotation curve, it's there, we keep it, and then we also look at gas and stars, and then model them. And then when we model them, we can solve the Poisson equation. And then by subtracting the velocities in quadrature, we get dark matter velocity. And dark matter velocity means dark matter mass. And we made a couple of assumptions, like we neglected non-circular motion, we had to make a structural assumption, our dark matter halo is virialized. And we went ahead, did all that for the 33 galaxies we had. We used a double exponential disk for gas, and we used the exponential disk for a stellar distribution that had a constant thickness. And this is what we got. We are looking at the difference between the model dark matter, essentially the extracted dark matter profiles, and the true one versus radius for all the 33 galaxies. So this is showing us how much we are deviating from the ground truth. So we see that the black line also is the median, and the pink lines here showing the 1 sigma scatter. Overall, we see that, we are doing a good job. It's like within less than 20% for most parts, which is actually quite nice in astronomy. But as we get closer to the center, things become more shaky. For example, on average, at 1% of virial radius, we are off by about 45%. And I should emphasize that, first of all, this is only the average, that is about 45%. There are galaxies that we can see that they are having way more deviation. And also, this is the error only caused by modeling, no observational error. Moving on, our second method is what I'm going to call it mass space. So when we got the total rotation curve, we're going to directly translate it into a total mass by assuming a spherical symmetry. And then again, we should model our gas and stars and then integrate their surface density profiles, get their masses, and therefore we can, And therefore, we can compare them with the total mass and get dark matter mass profile. Again, we made a couple of assumptions here. Some of them are the same as the previous method, but we are setting this assumption at different stage of our work. And then this is one of the examples that we did this mass modeling for. This is one of the galaxies in our sample. And the pink and orange are gas and stars models. Ones are in the dashed line, and the truth is the solid line. We can see that for gas and stars, in terms of their mass profiles, it's doing a good job. There is a little bit of shift and a few bumps, but overall it seems fine. And that translates into a very small mass deviation for the dark matter. We see it's almost following perfectly, except a little bit in the center. But we want to see, this is only one galaxy. We want to see that generally how good we are in modeling gas mass and star mass and then dark matter. This is the calculation for gas component and stellar component. So we looked at the gas mass deviation versus radius for all galaxies and also stellar mass. I start with this one. First of all, both of them has a trend that all of them has a good amount of matching with the truth, and there is an increase in the center, showing us things get very, very shaky at the center. But still, for stars, we are seeing an average of about 20% deviation, which is nice. For gas, is slightly more, it's about 35%. And now, how does this translate into dark matter mass? This is our dark matter profile. So the difference between the model dark matter or extracted dark matter profiles and the true ones versus radius is presented here. And the black line is the median. It's actually amazing. It's within less than 10%. Only at about 1%, we reach about at 1% of real radius, we are having about 10% error in extracted mass profile. But I have to say that this is only from modeling, and these are average numbers. For example, this system here is showing a very higher deviation from the truth, right? And it can go up to 30%. And again, this is only coming from modeling. Now, if I want to look at the two approaches side by side to have a better view of the overall understanding of how they differ, almost everything, they both have a similar trend, and in the central part, the error rises, which is expected. It seems that the mass space approach is doing kind of better, but that's not what I want to focus about. I want to look at this one. Although we are seeing that mass space is having a better match with the true underlying distribution. However, this is not a fair comparison, because when we use mass space method, we are able to use more complicated models, because solving Poisson equation for a complicated model, it's very expensive, and we cannot do that. And here, I'm not even trying to say that the exact same numbers will hold for the true dark matter profiles in the universe, but rather I want to say with this approach, we can evaluate the impact of assumptions we make. And based on the constraints you have and based on the kind of data that you get, you will end up having a degree of uncertainty, which is really, really dependent on the kind of mass modeling you use. And also, I should mention that these results are based on simulation. I don't want to say the exact same numbers are there in the universe, but this is an approach that you can evaluate your general offset from the truth. And finally, this is my conclusion. It seems that mass modeling techniques works pretty well overall for most part of the galaxy, except central part. In the central part, we need to be very careful about our structural assumptions, non-circular motions, and so on. And thank you, everybody. I will be happy to answer any kind of question. Yep. Start over here.
I have lots of questions. I want to talk to you later. But so all the plots you showed of the mass deviation were all absolute values. So
yes.
Systematic trend.
No, there is no systematic trend. We looked at that. There is no systematic trend. Even I checked that with stellar mass, like total stellar mass of a system, mass of systems. So if we say overestimate or underestimate for specific mass ranges, and there is no trend.
I have even more questions now, right?
Okay, I have actually a plot for that, I guess. I think I put it there. Yeah, so this is for the stellar mass, and we see that it's all over the place. But for dark matter, we made kind of the similar thing. But the only thing that I could say, which was interesting to me, was that we see way larger range of discrepancies when the stellar masses are higher, which is kind of expected, right? Because they could form a very, very thin disk, which is in a state of equilibrium, or also AGNs could be like really active and push things out of the center. Therefore, we expect more scatter there. Makes sense to me.
Do we have other questions? If I might ask one really quickly. So one question for your mass modeling method, you said, okay, we're going to assume it's spherical symmetry, but those were very disky galaxies. And so I would be curious to see how, maybe if you said, okay, let's actually try to assume more of a disk geometry to interpret, not just the, square GM over R, slightly different. If that would already cinch up, or how much of this discrepancy, was just due to if you've mismatched your mass profile assumptions.
Yeah, so in fact, we don't assume spherical symmetry for disk. We assume a spherical symmetric for the whole galaxy, which is mostly made of dark matter, which is a fair assumption, right?
Okay, but for this really small virial radii, I wonder if that assumption breaks down.
The assumption of a sphericity?
Yeah, if we looked at that on average for all the...
Yeah, but the thing is that we also looked at C over A for all these systems at all radius as a function of radius, and all of them seems to be, like, there is not much of a trend that halos get squished in the center. It's kind of, in fact, the opposite way around.
Okay.
Yeah.
All right, if there are no other questions, apologies, I lost slack a little bit. Let's thank Zahara again. And our next speaker is Nand Panisal. And he will be telling us about populations of subhalos beyond the virial radius, splashback versus field subhalos in fire. 2 minutes. This is forward, backwards laser.
So I actually changed the title of my talk a little bit, but the content is the same. I was just, yeah. So yeah, hi everyone. My name is Non Panitan Paisan. I know my last name is really long. And right now I'm a postdoctoral fellow joined between the Carnegie Observatories and Caltech, both located in the US. Today I will be talking about one of my most recent work. So I will be divided the talk into 2 parts. The first one I will be talking about the populations of backsplash dwarf galaxies in 5 simulations. And then in the second part, we will start to explore the origins of these backsplash dwarfs. So let's see. Okay, so there are a few keywords there. So what are backsplash dwarfs? So these are essentially dwarf galaxies that at the present they're locating beyond the very radius of the host galaxies, but they have spent some time inside the very radius of the host in the past. For example, in this plot, the x-axis shows the time in gigayears, and the y-axis shows the distance or the radius in kiloparsec, where the black curve shows the very radius of the host as a function of time, or R200m. So it makes sense that the very radius of the host grows as a function of time as the host is accreting more and more mass. And finally, the red curve shows the orbit of one of the backsplash dwarfs, where you can see for this particular dwarf, it was inside the very radius between 2.5 to 5 years ago in the past. So you might be wondering whether backsplash dwarfs are common, and the answer is that yes, they are actually pretty common, at least in cosmological simulations. We actually do see many backsplash dwarfs around individual Milky Way mass hosts. And the second class of dwarf galaxies that I want to talk about are field dwarf galaxies. So again, these are similar to the backsplash dwarfs in a sense that at the present day, they are locating beyond the very radius. On the other hand, the main difference is that they have not spent any time inside the host radius. So you can think of them as they are more or less pristine compared to the backsplash dwarfs. So the second keyword here is FIRE. So FIRE refers to a suite of cosmological simulations of zoom-in Milky Way mass galaxies, so similar to the NIHAO simulations that we heard about in the previous talk. And these, again, are hydrodynamical in nature, meaning that the simulations contain both the star particles, gas particles, and the dark matter particles. And because of the particle resolution, we think that we can resolve the dwarf galaxies down to about 10 to the 5 solar masses in stellar mass. This is just slightly below like the classical dwarfs, and we are just like pushing towards the ultra faint regime. So the question is, why do we care about backsplash versus field dwarfs now? First of all, the concept of splashback or backsplash radius is not new. Like a lot of cosmologists have tried to measure backsplash or splashback radius around in the context of galaxy clusters in order to constrain cosmology. However, we are trying to push this on a different angle. So we are only interested in like the backsplash dwarf galaxies around Milky Way mass hosts in order to gain more insight into the populations of dwarf galaxies within the Milky Way and the local group. And so the number of confirmed and candidate dwarf galaxies in the Milky Way and local groups have grown significantly within the last decade or so, with thanks to like many recent surveys, which are pushing the limit of our detection and discovery space to further and further away. And also we are able to detect the dwarf galaxies that are fainter and fainter in magnitude as well. So recently we have also detected like a lot of ultra faint dwarfs like that locate outside the halo of the Milky Way. And not just these two, but a lot of these dwarf galaxies seem to exhibit like some weird properties. Even though despite its distance, we think that they are more or less intact, but they exhibit some weird properties, such as like some of them shows that they are not quenched by realization, and some of them even shows like the evidence of ramp pressure stripping despite locating very far away from any large host galaxy. With this in mind, and with upcoming surveys like LSST, Roman, and Euclid, we are expected to be able to detect a lot of faint dwarf galaxies that are way beyond the very radius. So it is important to ask these questions now, whether are all the field dwarfs truly isolated, and if not, how many of them are backsplash dwarfs of either Milky Way or M31, and do they exhibit any different properties that would pose challenges in our attempt to model their properties. So we have identified both the backsplash and field halos around 7 different hosts in 5 galaxies. And note that I use the word halos here because I don't know if we can trust like the star formation physics to like these low mass regimes. So just to get a complete sample, we just identify all the halos, which are clumps of dark matter, regardless whether they contain star particles or not. And one of the things that I wanted to point out in this plot is that the number of backsplash halos seem to have a very large like host-to-host scatters. For example, M12R in the bottom right seems to have very fewer backsplash halos compared to other simulations like M12I, M12F, or M12B. So in terms of the abundance of backsplash halos as a function of radius, this plot, the y-axis show the radius normalized by the virial radius of the host. It seems that the backsplash halos are very common between like 1 to 2 virial radius, even within maybe 1.5 times the virial radius of the host. The populations of the overall halo seem to be dominated by backsplash halos. So next we are looking at the mass profiles or the mass distributions. The top shows the mass distributions of the backsplash halos, and the bottom shows the mass distribution of the field halos. Overall, we see that backsplash halos are more disrupted in dark matter mass compared to the field halos as expected. And I wanted to point out that the x-axis here is in log scale. So actually, on average, the median mass of the backsplash halo is only about 50% or less, a little bit less than 50% compared to the median mass of the field halos. And the second thing that we see is that the mass distribution of the backsplash halo seem to be more broad compared to the distribution of the mass of the field halo that seems to be more peak. So next we look at the radial velocity distributions. Again, top is backsplash and the bottom for field drops or field halos. So on average, the backsplash halos are moving away from us, so they are redshifted compared to the field halo, which seem to be in their first infall falling towards us. This is actually somewhat surprising because backsplash halos do not necessarily be like gravitationally unbound. They simply have the apocenter that is larger than the very radius of the host. So at some point they will reach their apocenter and turn around and fall back into the host. But I think it's because of the dynamical time scale of these orbits. So a lot of backsplash halos have not reached their apocenter and turn around and fall back into the host yet. That's why on average they're still moving away from us at the present day. So these plots show the distribution of the location of backsplash and field halos in phase space. Each panel shows one of the simulations, and at first glance, so it seems like the backsplash and the field halo seem to occupy different regions in phase space. So the x-axis here shows the distance and the y-axis shows the radial velocity. And in particular, it seems like the backsplash halos are more or less occupying some sort of its own filament, which I will call an outflowing filament. And all the field halos seem to also occupy another filament called, I will call it the infalling filament, due to its negative radial velocity. And I wanted to point out that the fact that the outflowing filament has a positive slope is kind of somewhat perplexing. This means that as we go along the outflowing filament to the larger and larger distances, these backsplash galaxies are moving away from us with higher and higher speed, which is kind of counterintuitive given like the standard picture of the infalling satellites. And I always like to think of this with an analogy with like a track and field sport. Like for example, we just had the Olympic Games, right? So think of like the 100-meter sprint, like all the runners kind of start at the same position and at the same time. And as time goes on, the faster runner will be able to cover larger and larger distances. So I think this is why it gives rises to the structure or the positive slope that we see here in the outflowing filament. And the fact that we see outflowing filament kind of give us a hint that all of these backsplash galaxies, or the majority of them, might be sharing some common origins, like something happened to them at some point in the past that create these outflowing filaments. So lastly, we were looking at the stellar velocity dispersion as well. So the x-axis is showing the stellar mass, and the y-axis shows the stellar velocity dispersion. And so the backsplash are shown in red and the field are shown in blue. They are more or less following the same trend across both of the groups. However, there are these like interesting few data points here that seem to preferentially sit at like a lower stellar velocity dispersion compared to other galaxies at the same stellar mass. And when we look at these galaxies in particular by eye, we see that these are backsplash galaxies that actually have disrupted stellar component as well. So they have diffuse stellar tidal tails, which because of the tidal disruption process, it might like increase the stellar sizes of these objects, or kind of induce like some coherent motion that cause the velocity dispersion to become lower. So I'm not sure how much time I have left. 2 minutes. So let's see. So I guess I will skip through most of the second part, which I will be talking about the origins of these backsplash dwarf galaxies. So first of all, we see that a lot of backsplash dwarfs seem to have the orbits that kind of coincide with massive mergers. In this case, like LMC mass mergers. they have like pericenters that kind of almost coincide in time with the orbits of the LMC. And we were looking at different things, including the orbital energies. We also look at the changes in the apocenter distances, but I wanted to show you the last thing where, because we have the entire cosmological simulations, so we can trace like what the phase space look like as a function of time or as a function of redshift in this case. So this is what happening. The movie is showing the phase space from around redshift like 0.8 or 0.9 up to about the present day. And what we see is that at the beginning, we see like one massive merger here. This one is LMC mass merger, and we know this because there is a clump in distance, but there is also a spread in radial velocity due to the internal velocity dispersion of this galaxy, and so which corresponds to the total mass of the systems, because this system is pretty massive, so the spread in along the y-axis is quite big. And as the merger comes in and goes through its first pericentric passage, it kind of start to form these outflowing filaments that we see here. And as time goes on, the filament kind of propagates outwards into the filament that we see today. So this kind of gives us a clue that massive mergers might play some roles in terms of creating the populations of backsplash dwarfs around Milky Way mass hosts. So thinking back in terms of the Milky Way, we also have like, the Milky Way has also have experienced massive mergers in the past, like the GSC or maybe Sagittarius or the LMC SMC as well. So maybe in that regards, maybe we do expect to find a few backsplash galaxies around Milky Way mass host. So I will leave my summary up here and happy to take any questions.
So,
Azi Fatahi, thanks, Don. I have two questions. I start with one, and if there's time, I go with the second. You showed that there's differences in the total mass distribution of these two populations. What mass definition did you use? And did you try something like Vmax, which traces more like inner regions? And did you still see some differences or not?
Yeah, that's a great point. So the mass definitions that we use were just the mass definitions from the halo finders, and in this case, Rockstar. Yeah, I know that there are newer halo finders that are probably doing better at assigning memberships to each halo, like the SimFi, for example. So yeah, I think it's a good point that we might be a good idea to try exploring different mass definitions. And yeah.
Hi, Nan. Nice talk. A related question. So the question I had was, is the mass within the half-light radius of these systems affected when they're backsplash galaxies? So I saw the 50% reduction in the halo mass, but does this translate to at the internal, I guess the mass within the half-light radius?
Yeah, so I have been thinking about how to best compare to observations, like what is the best definition of half-light radius in the simulations where we only have star particle informations. And I think maybe we can draw something like a radius that contain half of the star particles inside each galaxy. But in that regards, like most of these backsplash satellites are not heavily disrupted in stellar mass, and the tidal disruptions are more or less an outside-in process. So I would imagine if we take like observational effect into account, we might not see as large of a difference between backsplash and few dwarfs.
So I apologize. We'll have to follow up other questions on Slack and in person. Let's thank and Nand again. And our next speaker is Michael Fall, I guess in place of Aaron Ludlow. And he will be telling us about the impact of spurious collisional heating on the spatial distribution and kinematics of stellar and dark matter particles in simulated galaxies. So.
So the hydrodynamical simulations of galaxy formation are major achievements in our field. But they do have limitations, and it's important that we recognize those limitations, especially when we apply the simulations in contexts like this where we're comparing with data. They work in some contexts and they don't work in other contexts, and we need to keep that in mind. Now, the limitations that you're probably most familiar with are the ones having to do with the treatment of hydrodynamics, the treatment of star formation, the transfer of radiation through the galaxies. Many of the things like that are buried in the subgrid physics modules. And so I think you're probably all familiar that there are limitations of those sorts that you have to keep in mind. But there's a general tendency, I think, to regard the N-body part of the calculations, the ones that just handle the treatment of stars and dark matter particles, as being quite reliable. And what I'm going to tell you is that that's not true. And it's not true in a major way that affects the interpretation of these simulations. And so let me tell you about that. So keep this in mind. This is a schematic picture of a thin stellar disk, a rotating in centrifugal balance inside a spherical dark matter halo. And what's going on here really is that the dark matter particles and the star particles are interacting with each other pairwise, gravitationally. They're scattering off of each other. Now, the velocities of the dark matter particles making up the dark matter halo are moving much faster. And they're typically represented in these simulations by particles that have masses bigger than the masses of the stars. The stars are all moving around in approximately circular motions. The deviations from those are the random motions of the stars, and those are quite small. So what we have here really is a hot system, the halo, in thermal contact with a cold system, the disk. And just based on simple thermodynamics, we know what's going to happen as a result of that. The hot system's going to cool down and the cool system's going to heat up. And that'll keep going on until they both reach the same kinematic temperature. So this is an effect that will take place not in a galaxy whose dark matter halo is made up of elementary particles, but one in which the dark matter particles are massive enough to matter in a Hubble time. So we've set up a series of simulations, which I'd like to show you now, that illustrate this in a very simple, clean way. We've set up a series of simulations that look basically like this. We put an exponential disk in a NFW or Hernquist type halo, and we give the particles very small random motions in the disk to begin with. We keep the thing really simple, make it like an experiment that a physicist would love. There's no star formation, there's no inflow, there's no outflow, there's no feedback, there's nothing other than the interaction between these stars and the dark matter halo particles. And there's going to be a series of simulations, and I'll show you the results of that in just a minute, in which we keep everything the same. All the properties of the disk and the halo are exactly the same, except that we vary the dark matter particle mass and change the number of dark matter particles so that the total mass of the halo is fixed. That's the only thing that differs from one experiment to the next in this series. And here's the velocity dispersion now of the stars in the vertical direction in the disk for different cases of different values of the dark matter particle mass. So this is a galaxy that has a circular velocity of about 200 kilometers a second. The black line corresponds to dark matter particles of 1 million solar masses, then 3 million solar masses, 10 to the 7 solar masses, 3 times 10 to the 7th, and 10 to the 8 solar masses. And what you can see is that for the highest values of the dark matter particle mass, we're getting velocity dispersions in the vertical direction of the galaxy that are approaching the circular velocity. So this is no longer a disk galaxy anymore. This is an elliptical galaxy. And I'll show you the same simulations in a different way here. Let me see if I can do this laser printer. So there's a series. Here's the same series of simulations, left to right, just changing the dark matter particle mass from 1 million to 10 to the 7th to 10 to the 8th, and then in the in-between ones as well. And then running down here is time. These are the initial conditions. They're all nice thin disks. And then this is 1 billion years. This is 2 billion years, 4 billion years, and 8 billion years. And what you can see here is that if the dark matter particle mass is small enough, then we only get to a fairly modest amount of heating. The morphology of the galaxies change relatively little. You could certainly detect that observationally, and if a real galaxy were like that, but still it's relatively small. But by the time you get to 10 to the 7th solar masses, the morphology is changing drastically. And if you make the dark matter particles massive enough, they essentially just explode the galaxy. So there's nothing going on here other than two-body interactions between dark matter particles and star particles. Now, we've kept these experiments as simple as possible so that there's only one effect going on here in the simulation. Real galaxies are not like that. And galaxies in the cosmological simulations are not like that as well. So you might wonder, what relevance does this have to the simulated the cosmological hydrodynamical simulations? Many of these hydrodynamical simulations have masses in this range. The better ones, like the illustrious TNG, really only get down to 1 million solar mass dark matter particles. And so a lot of the simulation, like the TNG 100, for example, is going to be, whoops, has dark matter particle masses in the region of this middle section here, and magneticum and some of the others are actually like the far right ones, the more massive dark matter particles. So the question is, how relevant is this effect in the hydrodynamical simulations, where you've got a lot of other things going on as well? So here's a hydrodynamical simulation. These make beautiful pictures of the universe, beautiful pictures of galaxies. You know, how do they do that if this effect is important? And so to get at this question, we've run one of the Eagle simulations. We've run an Eagle simulation and a clone of this Eagle simulation that has 7 times higher resolution, or has a dark matter particle mass 1/17 of the initial one, but everything else is exactly the same. All the subgrid physics is exactly the same. All the parameters are set exactly the same. All the initial conditions are the exact same. Everything is exactly the same except the dark matter particle mass and the number of dark matter particles in the two, but kept such that their product, the product of the number and the mass, is the same in the two cases. And so now what I'll show you there is the results of this. So in this diagram now, there are 6 quantities plotted, and what's shown is the ratio of the quantity in the simulation with the highest the lowest resolution divided by the one in the highest with the highest resolution, and plotted against I think that's the dark matter halo mass. Okay, so less massive galaxies on the left, more massive galaxies on the right. And so what we've found in looking at these simulations is that there are some quantities that are relatively insensitive to this, and there are others that are quite sensitive to it. So the ones involving the gas particles are relatively insensitive. The reason for that is that the gas is being freshly accreted by the galaxies. It's coming in cold. So that's a cooling influence that counteracts the heating, the spurious heating by the dark matter particles. So the things that are closely coupled to the gas and the star formation in the galaxies, like the number of stars, the mass in stars, the mass in gas, the mass in the black holes, they're actually relatively insensitive to this effect. But all the structural properties of the galaxies, their velocity dispersions, their sizes, their shapes, are badly damaged by this effect. And so this is an effect that really does happen in the numerical simulations. And it turns out that the criteria for this to be important, it is in the isolated galaxy simulations, is very similar to the criteria that we found for the cosmological simulations. So in other words, the cooling effects and the heating effects from tidal interactions and so forth more or less cancel out. You can boil all of this down to a simple criterion about whether you have to worry about this effect in the simulations that you're using. And the answer is that as long as the number of dark matter particles in your halo, in the halo that you care about is more than about 1 million, you're safe. 10 to the 5th, not very safe, but if your standards of accuracy are relaxed, you might be able to get away with that. So you need somewhere between 10 to the 5th and 10 to the 6th dark matter particles per halo to avoid this effect. And if you really want to be completely clean of it, you go another order of magnitude up. That means that in simulations like Illustris and Eagle, Illustris TNG and Eagle, you can only actually trust the results of the simulations of the galaxies that form with dark matter total dark matter halo masses less than about 10 to the 11th or 10 to the 12th solar masses. So if you're using Illustris or Eagle to study the galaxies that are less massive than the Milky Way, you're in trouble. The galaxies more massive than the Milky Way are actually fine. But you need to be very, very careful if you're comparing things like the morphologies, the sizes, the velocity dispersions, the rotation velocities, anything to do with the sort of dynamical state of the galaxies. If they're in galaxies that are the Milky Way mass or below, you need to be very careful. You probably are not seeing a reliable treatment of the physics problem here. And I should just emphasize, this is not a numerical effect. This is not, this is a real physical effect. It would happen in the Milky Way if if the dark matter in the Milky Way were in the form of, say, black holes that weigh 10 to the 7th solar masses, we would not be living in a disk galaxy. We'd be living in an elliptical galaxy. So this is a real effect. It's very simple. It's just thermodynamics. I'm a little bit shocked that nobody noticed this after 30 years of simulating galaxies through these hydrodynamical simulations. It's sort of just really something we've noticed recently. Okay, thank you.
We start with the question here.
It's great talk. Just a quick question. So what code were you using for this simulations that you showed? And how is that related to those to the particle mass of the stars or like a baryonic mass? Because you say this is about the mass of the dark matter. So was there like a relation of like, you know, the ratio between like this baryonic mass and the dark matter mass the particle mass? So basically, I'm going to rephrase my question, is like, is there any dependence on the baryonic to the dark matter particle mass?
If it is, it's very weak. The main effect is how the basic effect, the basic physical effect is how discrete is the dark matter distribution? Is it a smoothed out, is it like made out of elementary particles where there are so many and they're so light that essentially you're talking about a very smooth galactic potential, or have they been clumped up into discrete objects which have much higher masses and therefore scatter the stars in the disk by much bigger angles and have a much shorter heating time, this is essentially a relaxation effect. And it's very insensitive to things like gas being around and that sort of thing. It's really all about how discrete is the dark matter halo distribution.
Yeah, very interesting talk. My question was very similar. I mean, in the isolated simulations, idealized simulation you were running, do you know what the stellar particle mass is? and what is the ratio between the dark matter particle and
Yes, I
this-
do. And we tried it for different values. It doesn't make any difference as long as it's a very weak effect. It's a very weak effect. The primary effect, I mean, essentially for most of these, we're almost in the test particle limit. Okay. But it's an effect that you cannot get away from by setting the dark matter particles and the stellar masses equal. Okay, because you still have the high random velocities of the dark matter particles, so their temperatures are much higher even if they have the same mass. And that's the main thing, actually, is having a system with a higher temperature and this amount of discreteness in the potential.
Okay, I think we're going to move on to our lightning talks. Let's thank Michael again. So our first lightning talk is going to be from Ji-Hoon Kim, The Formation of Light-Type Galaxies, Nature versus Nurture.
So while everyone is observing what Michael said, I need to give this flash talk. So I'm Ji-Hoon Kim from Seoul National University. Mind you that there are two Ji-Hoon Kim at Seoul National, one without hyphen, numerical simulation guy, and the other without hyphen, an observer, which is me. So this morning, Enrico and Michael gave wonderful talks on Michael's actually namesake relationship, force relationship on late-type galaxies and elliptical galaxy altogether. And I will actually look further into within the late-type galaxies if there is any systematic difference or dependency on central surface brightness. So, yeah, I have just one slide. So basically, if we want to see if there is any reason for like CDR, central density relation, to happen for the disco galaxies. Keep in mind that when I talk about lower surface brightness galaxies, this is referring to the central surface brightness of disk, exposure disk, rather than average surface brightness or anything like that. Especially with the emergence of ultra diffuse galaxy, UDG. UDG and low surface brightness galaxy has been like interchangeably used a lot. I'm not gonna say this is like a real problem, but there you have to be very careful about which galaxy population you actually talk about, since just like pick up the the LSBG with like average surface density would be contaminated by lots of like bulge component or something like that. So here with the Spark data, we actually plot again force relationship in the middle on the top. Basically, you are seeing at the the high surface brightness galaxy, intermediate surface brightness galaxy, and low surface brightness galaxy from red, green, and blue. So in fact, this we classify these galaxies into these three categories actually based on baryonic mass surface density. Actually, low surface brightness galaxy, which is actually lower than 200 mass solar mass per square parsec. See, there's some tendency for LSBG to have a higher specific angular momentum, only up to 10 to the 10th solar mass, which is actually reported by Salinas et al. And Post et al. But actually, even more massive than 10 to the 10th solar mass. Actually, the tendency is kind of flipped, so you don't see any tendency for that. Even further, actually, angular momentum or spin parameter don't have any correlationship with central surface density, if you as you see from the bottom panels. So it is very interesting to see how actually we got to that point. So moreover, actually we found that actually there are some discrepancy between like proxies for spin parameter. So we decide to actually measure spin parameters rather than just using proxies for spin parameter. And then moreover, also we actually try to measure. Although actually Federico mentioned that all those samples are kind of isolated, like not within any 4 megaparsec of other galaxies, but still we want to kind of like quantitatively evaluate the the flipping the tendency for angular momentum to see any kind of, the relationship with the galaxy environment or something like that. So stay tuned. Thank you.
Thank you. And our last lightning talk for the today is Nikhil Arora.
Hi, everyone. I'm Nick. I am a postdoc at Queen's University. And in this project, I am trying to quantify the impact of AGN feedback on dark matter halos. Better? Up? Good. So we use the Nihao simulations to do this over a stellar mass range of log 9.5 to 12. So basically dwarf galaxies, Milky Way, and massive galaxies. The plots that I'm showing over here are mainly for the Milky Way type galaxies. And so there's two major things that we find. The first one is shown on the left, which is kind of showing you how much dark matter is suppressed as a result of AGN feedback as a function of radius over 4 different redshifts. And what you see is for Milky Way type galaxies, these things continue, the dark matter suppression continues to grow as time goes on. And it sort of taps out at roughly at around 40%. And on the left-hand side, that's the right? Yeah, on the right-hand side, I'm showing how far spatially is this effect seen. So this is mainly just the correlation of the amount of dark matter that is suppressed as a function of the black hole mass. And what we find is this happens to be around roughly 5% of the virial radius. This is quite interesting because it contains nearly all the stars in these halos. So yeah, so I also have a poster somewhere downstairs. If you're interested, check it out. And I'm here to chat if you.
Awesome. And let's thank all of this session's speakers again. And I believe we're back here at 10 a.m. On Thursday. Or sorry, 10 a.m. is the poster session downstairs, 10:30 here. So thank you again to all the speakers of the session.